Okay, maybe let's start. So how did you find yesterday's lecture? It's very introductory, right? So today we will cover like more methodologies and all those kind of things. Yeah. So hopefully you will get some insights, and then you can try to apply similar approach into your research. Yeah. So yesterday, if you remember, like there were 4 lectures, right? 1, 2, 3 was by me and 4 was by Dr. Moumita. So today I am going to cover lecture 5, 6 and some part of 9. Okay. The reason being, actually 9 was about joint consideration of security and sustainability. So if we are going to cover already security, I thought I will cover briefly that part as well. Okay. We will come back again to that part, but briefly I will cover. Okay. So also I would say there is some change. Yeah. So lecture 7, that is about system design methodologies for sustainability, was today. Okay. But I am kind of moving it tomorrow. So everything about security today and everything about sustainability tomorrow. Yeah. So because initially I thought I will do security, sustainability, then do mix up. Yeah. So we will cover mainly security. That is why you can say from the outline is like system design methodologies for digital security 1, 2 and analyzing methodologies and joint considerations. Okay. Now you already have seen this. Yeah. What can be different categories of attacks on electronic devices. So I have brought it again just to tell, like we are going to cover some into this and we are going to cover some into this category again. Okay. Okay, so in the previous one you saw there was on the left hand side physical and side channel attack. Yeah. So it is not really getting the information directly, rather using some physical properties. Yeah. So how this is typically done? Yeah. So in typical scenarios you will see like you will have some input ciphertext, yeah, which means there is a text that is encrypted and it is sent. Yeah. And then you do the decryption at the receiving end and you get the plain text. Yeah. This is how it typically happens. But as part of side channel attack, so when the decryption is happening, you can try to extract some side channel information. Yeah. So like what is the power consumption? Yeah. What is the maybe electromagnetic radiation? What is the sound level? Yeah. And then you can analyze these information, and then from this also you can get the kind of encryption key. And if you get the encryption key, you can get the plain text as well. Okay. So this is how typically this side channel attack is done. Yeah. So main purpose is typically to find the key. Yeah. And like I have said, if you are encrypting with different keys, yeah, like maybe different length, and then your side channel information will vary. Yeah. There could be high power label, low power label and all those things. Okay. So this is how side channel analysis, it finds out the key, and then you can always get the plain text. So the left branch actually can also be called as like hardware level security attacks. So you see, like we are using some hardware properties, yeah, not really direct information. That is why some people categorize this as hardware level security attacks. And these ones are expected to rise in future, and mainly due to 2 factors. So the first factor I would say is hardware Trojan insertion. Yeah. So you see, like there are a lot of electronics manufactured. If someone wants to have attack on some system, like from one country to another country system, engineers or someone from inside can insert hardware Trojans. Yeah. When things operate, they let the whole system down. Okay. And the main reason you can guess, it's due to excessive outsourcing in hardware supply chain. Yeah. So not everything is done at one place. So many things manufactured at different places. Yeah. like CPU, GPU, memory, all different companies, and then it goes into one. Yeah. So if everything is at one place, it's much better. That is why you can also see lots of countries are trying to kind of secure supply chain. That means they want to manufacture just there, okay, not rely on outside world. Yeah. And if this kind of things happen, basically they can cause denial of service of various types. Yeah. So it's like whatever you want to do, you cannot do. So that's one of the factors. And the second one is the rapid increase in the number of connected devices. Yeah. So imagine if my laptop is not connected with internet, nobody can attack. Yeah. There could be physical tampering, they can do reverse engineering to get some information, but if it's not connected, nobody can log in. Yeah. Or nobody can put any virus or something. So because of the connectivity, we are facing all these issues. Yeah. So connectivity provides some advantage, but it leads to a lot of problems as well. Okay. What it does, so it makes it feasible to craft and insert malicious programs through various upgrades. Yeah. So like you can see sometimes you get notification like update is ready. Yeah, because it is connected. So when you do those upgrades, there could be some malicious program encapsulated into that update, and then they can start doing some denial of service or leaking some information. Okay. And these programs, I mean, typically you can say can leak physical attributes. Yeah, like again I said power, temperature, and they can do basically in a covert fashion. So it's like maybe the power label of my laptop is being sent, but I do not know. Yeah, because it's like at quite different frequency at which it is sent. So that is why it is called covert leak out. So nobody notice it. Okay. So these can be sent, and then attackers can use this to decode personal or national defense data. Yeah. So if it's like kind of national defense system, those are the main targets. Yeah. So that can be very fatal. And if you are covertly leaking out physical attributes, this is called covert channel attack. Yeah. There is a covert way to transfer the physical attributes. That is why covert channel attack. Okay. Now let's look on covert channel a bit more. So what is the communication media typically in these? Yeah, we already have seen some. So there could be heat transfer. Yeah, so like temperature transfer from one place to another. If it is temperature, we call this thermal covert channel. Yeah, short form is TCC. Okay. Timing can be another communication media or another side channel property. Later on we are going to look each of these one by one. Yeah, how this thermal covert channel can be used, how the timing can be used, and it could be inaudible sound as well. Yeah. So for all these three, later on we are going to see how exactly the attack can happen. So again, inaudible sound is like it's being again covertly transmitted, but nobody can hear it because the frequency at which it is transmitted is inaudible. Yeah. Okay. I think I'm putting a question here again. So we have seen these communication medias, right? Can you think of any other communication media? I don't know if you get, again you can use your phone. Yeah. Let's see if it's working or not. I think I need to go there again. So it's not working, right? Just give me a second. Hopefully this one, yes, I think it's working. So any other communication media you can think apart from temperature, timing, inaudible sound? Anything you can think of? Okay, body language, that's interesting one. Okay, yeah, I think energy, yeah, energy can be another thing, like power, you can send the power level. Yeah, I think body language, yeah, can be interesting. Or you can also think like, you know, sometimes there are ways people can find out what exactly you are speaking, yeah, just by the lip movement or something. So it's kind of some kind of movement, yeah. But this needs to kind of we need to somehow relate with a computer, yeah. What could be the body language? Yeah. Okay, frequency can be one thing, yeah. I think frequency can be another. I think frequency is also related to power. Yeah, you can say like if the processor or core is operating at certain frequency, it has some power level. Yeah, so they are related. Sign language. I'm not sure how to use it. I don't know if you can explain. Yeah, whoever typed it. Yeah. Maybe there is a way. Yeah. Okay, acoustic signals. Actually, acoustic is typically interchangeably used with sound, yeah. So it's the same. Okay, there are a few other ways like electromagnetic radiations, yeah. Each electronic has some radiation level, so that one can also be used. Okay, good. So you have some nice, interesting ideas. Okay. Okay, sorry, I think I need to log out this one and go there. Okay, so what are the advantages of covered channel? Yeah, you might have seen other attacks, but covered channel has some advantage over other ones. Okay, just give me a second. Okay, so they do not rely on shared resources, cache and memory. So if you can see, like there are lots of attacks that happen because there is a shared resource, yeah. But this one does not rely because it can secretly leak some physical attributes. Okay, and this also does in a wireless manner, yeah. So like I said, you covertly leak something, and then nobody can notice. Okay, so this can be like dangerous, yeah, nobody can find it out. Okay, so now let's look, like I said, I will look one by one. So let's look first this hardware Trojan based attack. Okay, so in that we are going to look hardware Trojan assisted power budgeting system attack, and this power budgeting system attack is for many core systems. Okay, so you know, like to these days most of the processors are many cores, right, or multi cores. They're like 8, 10, 20 cores. Okay, so in that we can do something like power budgeting system attack or power budgeting attack with the help of hardware Trojans. Okay, so what is power budgeting in many core system? First let's look that. Okay, some kind of introductions of that. So like I said, this could be like a processor into your smartphone, like an 8-core processor, yeah. So this is many core, means there are like 8 or 10 cores. Okay, so what is power budgeting here? So here all the cores from 1 to 8 are constantly competing for their shares of power out of the maximum power available for the chip. Yeah. So if you take a processor, it's kind of said what is the maximum power level. Yeah. So our phone has like around 10 watt, the CPUs in the laptop, they have like 20 watt, but desktop ones, they have like 65 watt, something like this. Yeah. So that is the maximum power available, but if you want to run something on each, so that 65 watt has to be shared amongst all these, right? But if you want to do something on any of the cores, it has to request like how much power it can get from that 65 watt. Okay. So this is like, this always happens in our processors. Okay. And to kind of find out how much exactly should be given to each core, there is typically a budgeting scheme. Yeah. So that efficiently allocate power to achieve the highest possible overall performance. Yeah. So even if like maybe this core is requesting I need 2 watt, but it might not get 2 watt. Yeah. It might get maybe even less, because other cores are going to give better performance overall. Okay. So this is like power budgeting. Okay. So now let's look some example. Yeah. So this is a 3x3 multi-core system or many-core system. Yeah. So what happens here? So when a core wants to run some applications, okay, let's say this core B, yeah, it wants to run some applications. So what it will do? So it's going to send a request to one of the cores that will act as a manager. Yeah, because out of all the systems, there is one that is manager. Yeah, it's managing everything. So if core B wants to run something, it will send a request. So here let's say core A is the manager core, and this request will go in this form. Yeah, and then this manager core is going to return the power budget that it can use. Yeah, and power is directly related to frequency. Yeah, so you can say like if it says I want 1.2 watt, that is equivalent to 2 gigahertz. So the manager is going to kind of return a response to core B just to say you can run at 2 gigahertz. Yeah, but it might be it cannot get that much. Yeah, because other cores are also requesting. Okay. So here manager makes decision based on all the requests that are coming from all the different cores, and it makes the allocation in a way so that overall performance of the system is maximized. Okay. So this is how this happens in our processor as well. Yeah, there are so many cores, each of them need to run at certain frequency or power level. They all request based on what is on them, and then manager decides how much power can be given to different cores. Okay. So this is how power budgeting happens in many core systems, and this is one of the example.
So in real systems, are they working as like you have one manager and other like master slave, or they are working on some different mechanism?
Mostly it's like
core systems that are presently available.
Mostly it's like this. So there is a manager that manages everything. Yeah. So even like in our smartphone, yeah, there are like 8 cores. Yeah, but the operating system will be running on one of them. So it's not using all of them, or maybe 2 of them. Yeah, so, but typically it's one of them. So that core is like a manager. Yeah, the request goes to that, and then it decides. Yeah, so the manager core means simply it's not really the core, it's the kind of system that is running on that. Yeah, or the operating system that is running on that. Okay. Yeah. So this happens in our laptop as well. Okay. Yeah, please feel free to ask questions, yeah, whenever you have any. Okay, so now let's look how a hardware Trojan assisted power budgeting attack can be done. Okay. So we have already seen this one, right? So this one is normal situation, there is no attack. So core B requests its power budget, and it goes to the manager A, and then it gets some kind of response. Yeah. So here it says you can run at 2 gigahertz. So this is the typical operation how things will be running, yeah. But let's say on core C, or there could be a router that connects core C, yeah, there is a kind of hardware Trojan, yeah. So what it can do? So basically when you make a request, it can simply change the request, yeah. So let's say it says I want 1.2 watt, but this Trojan changed the request to 0.1 watt. So at the manager for this one, request will be for less watt, yeah, and because of that it will not say you can run at 2 gigahertz, it will say you need to run at 1 gigahertz, okay. So you can see like now whatever power it needs it cannot get, because there is a hardware Trojan in the middle that changes the requests, okay. So this is one example of hardware Trojan based attack, okay. And if this happens, you can simply say this results in denial of service attack, yeah. So like maybe it wanted to do some critical task, now it cannot get the frequency label or power label, so it cannot do with the same performance, yeah. And maybe if it's kind of a critical system like a car or something, so like you wanted to apply brake and the brake control will run on one of the cores, yeah, and then maybe the moment you press the brake and the moment it really happens, it might be much delayed, yeah, okay. Later on we are going to see a bit more on this kind of examples, yeah, but simply I hope you get, yeah. So whenever some request goes from a core to the manager, if there is hardware Trojan in the middle, it can change the request, okay, and thus the core that is requesting, whatever it is requesting, it will not get what it wants, okay. It can be in real life as well, right? Like we sometimes request something from some places, right, but there are people in the middle, they can change it, yeah, and then you get different response, yeah. There could be people with malicious intention, yeah, okay. Okay, so there we saw there was one hardware Trojan, yeah. So now I just have put a question, what do you think can happen if there are multiple hardware Trojans? So let's say this is also kind of has hardware Trojan and this one also has hardware Trojan. Okay, I think I need to, I don't think you can see, right, on the, let me go to that one. Okay. So what I mean, like, you know, with one hardware Trojan, the request was changed, right? But let's say there is hardware Trojan on second one as well. So what can potentially happen? Yeah, so the more cores will be affected, yeah. Anything else you can think? So multiple critical tasks delayed, yeah. So it's like if there is a request from multiple places and there are multiple Trojans, all of them will change your request, yeah. The first one maybe said 1.2 watt to 0.1 watt, yeah. But if there is Trojan here, this can change it further, yeah. It can say maybe again 0.1 to 0.01 watt. So the request can keep changing, yeah. So you can see this is kind of more problematic situation, yeah. Okay, multiple interrupt requests. Multiple Trojans can block the multiple communication ways and make system request completed, delayed or blocked, yeah. Behavior of the overall system would be more erratic, of course, yeah, like whatever system wants to do, you will never be able to achieve because always the requests are changing, okay, yeah. Short circuit, okay, I mean could be possible, yeah. So for example, let's say you requested 1.2 watt, right, and this whole chip has like 65 watt, right? Let's say you requested 1.2, but it gave you like maybe 20 watt, and then it can heat up too much. Yeah, it's like too much extra power. Yeah, so there could be short circuit. Yeah, that's possible. Yeah. Okay, good. Okay, let's see the next one. So we have seen this. Oh. Just give me a second. I think there's something wrong. Okay, so how now that can be detected, right? If you want really stop, that has to be detected, right? So at the moment I would say do not look this part, yeah, just look on the left hand side. Okay, so let's say you had this 4 cores, yeah, A, B, C, D. This one requested 1.4 watt, this one 1.3, this one 1.2, this one requested 0.1, yeah. So this is like one approach. It can be how you can detect. So you can take average of all these, yeah, and then you can do some calculations like this. So like how much is the deviation from the average? Okay, so you can say average minus original request, yeah. So this is the original request. So for A it will be 0.9 watt, right, because average is 1 and request is 0.1. Similarly for B it will be minus 0.2. Okay, so these will be the kind of deviations, yeah. Now you can kind of develop some threshold. If you say if your deviation is more than certain value, you can say this is potentially an attack, yeah. So let's say greater than threshold, and this threshold can be 0.4 watt, and then you can say there is a hardware Trojan attack, yeah. So thresholding based mechanisms are always used, yeah, in a lot of places. So how this is how you can detect, yeah, but how you can stop it, yeah. So stopping is on this side. Now you know this core is infected, yeah. So now you can do another average, but do not take the power value of the infected core, yeah, because it has been reduced too much or it has been increased too much. Then you average only uninfected cores, yeah, and this average is 1.3 watt, and based on this average you can do another distribution, yeah. So you can see like this one was originally something, but it became infected, but then with some reset you can allocate higher, yeah. But when you do this average in the defense, do not take the power label or the request power label of the infected core. Okay, so this is one very simple, yeah, like thresholding mechanisms, yeah. Okay, all right. So this is this was developed by one of the PhD student in my group. I will tell you a bit more about the paper that it has, where it was published. Let me see. Again, I think I have some question after this. Okay, so thresholding was one method to detect it, right? So can you think of any other method? Any other idea you can think of to detect and then mitigate it? Yeah, so detection means you find the infected core, and mitigation means you correct its power level. Okay. Always maybe try to think from different places, yeah. Any ideas, anything you can think of? So I also had not thought yet. So I just want to discuss with you. Yeah, what's your thought? Limit the change in power request by setting a threshold. That's interesting one. So it's like when the requests are made, yeah, if it goes 0.1, it's obviously it is infected, but you can say no request can be less than 0.8 watt or something like that, yeah. So you can set the limit, yeah. So this one is kind of a direct defense, yeah. There is kind of you can say it's like security by design, yeah. So it's not letting that happen, but this is interesting one, yeah. Frequency behavior analysis, detection and mitigation. Okay. I think like we said, yeah, when the request is made, typically in return it is the frequency level, yeah. So of course that can be analyzed, and then it is sort of something similar, yeah. You have to say like if frequency level is kind of returned by the manager core is very, very low, there is potentially an attack, yeah. Okay. I think there could be few other things. So if you remember, like we were saying, there is a request going from different cores, right? So you can look like what is the load of the request, yeah. Maybe that core needs to run some very compute intensive application, yeah. That means it typically needs high frequencies or high power, yeah. There could be some core that doesn't need to run very compute intensive application, so its request can be low. So kind of the response that you get, you can always think of relating it to the workload that it wants to execute, yeah. If the difference is too much, yeah, like you are going to sacrifice too much in the performance, then you can kind of say potentially there is an attack, yeah. Okay. So it's like, for example, you request maybe from a bank some ATM machine, yeah, some cash or something, yeah. If you get in return, like let's say 1000 you requested, but if you get 800, 900, maybe it says the machine has something wrong, you can say this is fine, yeah. But if you just get 100 rupees, then you can say potentially something has gone wrong, yeah. So it's like what do you want if that differs too much based on what you get, yeah. Okay, that's good. Okay. So we have done this one. Okay. So now let's look some results, yeah. Like what kind of things are impacted as a result of this hardware trojans present in the chip. So the first one, okay, so the first one is called something like infection rate, yeah. So like how many requests are infected, yeah. Let's say in the system, maybe over certain time when the applications are running, maybe 1 hour, the requests keep going to the manager, yeah, from all the cores. But then lots of requests are modified, yeah. So this can be said like infection rate, yeah. So if half of the requests are modified, you can say infection rate is 50%, yeah. So out of 100 requests, 50 are modified, okay. So this is something, one metric that can be used, yeah. So now let's look this infection rate with respect to the number of hardware trojans, yeah. So like in previously I said, yeah, if there is 1, if there is 2, if there is 4, yeah. So definitely that one is going to increase the infection rate, right? It's going to modify more and more requests, yeah. And after certain point, for this system that is 64 cores, yeah, or you can say 8 by 8, if you have like 10 hardware trojans out of 64, then around 50% of the requests will be modified, yeah, that means they are infected, okay. And here there is one more, there are like two plots, yeah, so you can see one is the global manager is in the center, yeah. So you can see we saw the manager was at one corner and request was going from another corner, but global manager can be in one corner, can be in the center as well, yeah. But you see, like if the global manager is in one corner, so the blue line, yeah, the infection rate will be more because it has to travel a lot, yeah. But if it is in the middle, the infection rate will be less, yeah, because it can request can reach to the global manager much faster, yeah. So imagine in though that 3 by 3 system, yeah, if the global manager is not the top left but the middle one, yeah, so all the requests from different one are going just next to it, right, then there is no point, no place to kind of modify the request. So that is why you can see if it's in the corner, infection happens much more, but if it is in the center, infection happens less, okay. So this is with respect to a number of hardware trojans for a system of size 64, but you can also increase your system size, yeah, maybe it has 512 cores, yeah. So there are some processors in the market with thousands of cores, yeah. So in this one you will see like to reach the same infection label, you will need to have more hardware trojans, yeah. So for example, whatever you could achieve with 10 trojans here, you need maybe around like 30 trojans, yeah, because the system is much bigger, okay, yeah. Okay, after this I have a question. So what do you think of the placement of hardware trojans, whether it's going to impact the infection rate or not? So you know the hardware trojan again can be in the middle, can be somewhere, right? So whether it's going to impact the infection rate or not. I think I have a question slide, yeah, let me try to go there. No, not this one, sorry. I think it will not run like that one. So just the simple question is, do you think placement of hardware trojans will impact infection rate? Yeah. So like placement of the global manager, yeah, where all the requests are sent, it changes the infection rate, right? Similarly, hardware trojans can be at different places, yeah. So do you think that one will also change the infection rate? I would say yes, yeah, because again like global manager, if where exactly is this one, if lots of requests are passing through that, then it will change much more, yeah, but if less requests are passing through it, it will change less, okay, yeah. So I think my next question is around that line. Okay, so let's say these trojans are around the center, yeah, maybe 2, 3 or 10 of them, and they can be distributed randomly in the whole chip, yeah, or they can be in one of the corners, yeah. Let's say the 64 cores, yeah, 8 by 8. So in one of them everything is around the center, yeah, maybe 10 cores in the center are infected, and then in another one all these 10 can be distributed, yeah. And in another, all these can be in one corner on the left hand side, top left or top right, yeah. So what do you think will be the kind of value of infection rate? So in which case do you think it will be highest, or in which case do you think it will be the lowest? Yeah. So if you can say in this case infection rate will be highest, and in that one, in another one, which one infection rate will be the lowest. Anything typed? Oh, it's not yet here. Okay. Maybe some internet issue, I don't know. Did you type? Some of you typed? No. Maybe internet is not working very well. Okay, let me ask in a different way. Yeah. So let's say if all the hardware trojans are in one corner. Yeah. So do you think infection rate will be highest or lowest? It should be lowest, right? Yeah. So which one will be highest? In center one, yeah. Because typically all the request has to go through the center. Okay. Yeah. So now you can think of like you want to attack a system, yeah, that has many cores, yeah. So you know like where exactly to plant these hardware trojans to have the maximum impact. Okay. All right. Now let's see some comparison results. It's very slow. Some performance issue with my laptop. Okay. So infection rate comparison, yeah. Like I said, hardware trojans are around the center and they are distributed randomly and they are in one corner, yeah. So let's now first look one system, yeah, this 64 cores, okay. What will be the infection rate? Yeah, like you already can guess, if hardware trojans are in the center, that will be highest, yeah, and if they are in one corner, that will be the lowest. Okay, in randomly distributed, it will be somewhere in the middle. Okay, now here is the different system, yeah, but there is kind of to have more and more results. So this A represents a case where out of 16 cores, one of the core is infected with hardware trojans, yeah. So 1 by 16, yeah. So if it is 64, that means 4 hardware trojans are there, yeah. If it is 128, so you can simply divide 128 by 16, so that many hardware trojans, yeah. So that is why you can see maybe this graph is more or less the same, yeah, because as the number of cores are increasing, the number of hardware trojans are also increasing. Okay. In the second one, so here 1 core out of the 16 is infected, here 1 out of 8 is infected, yeah. So you can see the number of hardware trojans or infected cores are double, yeah. That is why you can see the infection rate here is this much, but here it's very high, okay, because the number of hardware trojans are just double, okay. So the infection rate, you can't say it's exactly double, but more or less much higher, okay. But this trend is always there, okay. All right. So fully now you know if you want to attack a system that has multiple chips, this is how you do, okay. Or think of another system like a data center, yeah. So again, when there are a lot of servers in the data center, there is a topology that is followed to connect them, yeah. So again, if you want to let the whole system down, you have to think you should attack something from where lots of information is flowing, yeah, not something in the corner, yeah. If you can attack something that is on more centralized position, that will have more impact, okay. And I think yesterday I told you, like, if you want to be the best security expert, develop the best defense mechanisms, it's best you be the best attacker first, yeah. So think of attacking the systems in all the possible ways, yeah. And this is how a lot of companies do, yeah. These security companies, they have a lot of attackers. So they keep attacking systems and I mean, it's kind of in an ethical way they do. They don't harm anybody from the companies, but then they develop the defense based on what they think all the possible attacks can happen. Okay? Okay. Now let's look another metric like applications performance changes. Yeah. So because a request is going, yeah, from one core to the manager, and then it is getting modified, yeah. So in this case we are assuming like there are two attackers, that means two hardware trojans, yeah, and then that means there will be, and there are two victims, yeah. So like two cores are requesting, yeah, and there are two trojans present, okay. So here what will happen, like the victim cores, like you have seen, their power request is reduced, yeah, typically. So those victim cores will have reduced performance, yeah, and this, as there is more and more infection, their performance will keep decreasing, yeah. But these attackers, the trojans, they can, for their own request, they can always ask for more power, yeah. So they can boost their own performance, yeah. So this is just to create some kind of disturbance in the system, okay. Similarly, this is another scenario. So here we took some kind of mixture of some applications from some benchmarks. Here is another mixture of application, just to kind of show it works with all the applications, yeah. So mixture means there are lots of applications running on one core, core 2, core 3, core 4, like that, yeah. And out of that, two of them, we are assuming there is hardware trojan, and two of them are making the request to the manager, okay. So this is how the performance will change, yeah, okay. Okay, hopefully it's clear, yeah. Okay, now I have a question, yeah. So will there be impact on other metrics than performance? So PC performance, right, it reduces, yeah, of typically the victim applications or victim cores, yeah. So can you think of any other metric that will also be impacted, yeah. It might be basically increasing in value with the hardware trojans, yeah, or it can basically reduce, yeah. I don't know if you can see the screen. No, you see the previous one, right? I think from PowerPoint it's not working. Let's go next one. Yeah. So will there be impact on other metrics? Efficiency, I think it depends how you relate to efficiency. If it's performance, of course, yeah. Or you can say overall system performance, then also timing delays. I think again it's timing delays, I would say is related to performance, right. It's like if one of the core wanted to have higher frequency but it cannot, then it's going to run at lower, yeah, and this will impact the timing of the applications, and that is why that will result into like lower performance, yeah. The reliability, that could be interesting one. So you know, like this Trojan can cause some reliability issues as well, yeah, because it's just sitting in the middle and doing something extra unnecessarily, right. That means using part of the chip more and more, yeah. So it can basically do some kind of you can say like heating of the chip, or something else. Yeah, so it can make the whole system less reliable. Yeah. Okay. So heating, I think we covered. Setup and hold violations. Yeah. So it's going to violate. Yeah, like what you want to do. I don't know what you mean by setup and hold. Yeah, not sure about it. So communication cost and computation cost. So communication cost is like, again, the requests are being modified, right? So it could be like when the request is modified, the number of bits in the packet change. Yeah, could be, but we have not evaluated that. Yeah, so it could be it can cause more communications. Yeah, okay. So make the chip lifespan shorter. Again, this one is related to like if the chip is operating at higher temperature. Yeah, if there's a lot of heat in the chip, so that will make the whole chip basically to fail as quickly as possible. Yeah, okay. So this is possible. Yeah, but in our work we have not evaluated all the things. Yeah, but you can think like these Trojans can have these kind of impacts as well. Okay. Yeah, good. Okay, we saw this one. Okay, so any questions on the Trojan part? Yeah, I think I missed to mention the paper. So we have a paper in a journal and in a conference as well that has evaluated all these. Yeah, I think you can look on my website. Yeah, I think I don't see here including it. Yeah, questions?
Like the hardware Trojan, like the hardware is different, or
So,
like it is programmed differently.
so you know you when you build the hardware, you just specify like how many transistors and all those you need at different place. So Trojans are just kind of a circuit that is designed in a way it's going to trigger at some point when the maybe that part is used maybe after 1 year or something. Yeah, so it is designed in a way like it waits maybe for some cycle counter. Yeah, or some timing. It doesn't do anything until certain point, but then it triggers at some point, and then
There is no way like it is smart because it is only hardware. No software programming is done.
yeah, so it's mainly hardware. Yeah, yeah. So I don't know if you know, like the lot of fighter planes. Yeah, sometimes aeroplanes they have just crashed or disappeared. Yeah, so some people believe it's as a result of hardware Trojan. Yeah, maybe fighter plane was used for 5 years, but then someone put these Trojans in a way it will trigger after this much of time. Yeah, so there could be many ways to trigger it. Yeah, so there's a circuit that will trigger at certain situations. Yeah, maybe after 1 year, or maybe when the temperature of the chip rises this much, and these cannot be detected in the typical testing when the chip is produced. Yeah, yeah. So this is like just kind of circuit designed in a way that will work not now but rather after some point. Okay. Any other question? Yeah. And the fear is like, you know, like I said, why they are coming into picture. It's huge supply chain issue, right? If countries want to do war, yeah, they might sell some electronics to some other country that might be used in some critical systems, yeah, or defense system, and they may implant this hardware Trojan, and at some point this whole system can go down. Yeah, that is why you can see like every country now wants their own manufacturing, semiconductor manufacturing place. Yeah, they don't want to rely on anybody else. Okay. Yeah, good. So if you remember, another one we said is we are going to look is Just give me a second. Oops. Another one we said is covert channel attack. Yeah, you remember I said you can covertly leak some physical properties. Okay, and I said we will look some of them. Yeah, like how you can leak temperature to get some sensitive information, how you can use sound to get sensitive information, and how you can use timing to get sensitive information. Okay. So first of all, let's look thermal covert channel. Yeah. So at the name says it is temperature. Yeah. Temperature or thermal means heat. So this one uses heat as a media to secretly leak information. Okay. So how it is done? So there is a transmitter, yeah, that will send the sensitive data via the heat. So that means like it could be like something is happening in my laptop, but there could be another receiver here that has a temperature sensor. So if my laptop becomes hot, this receiver will read its own thermal sensor, but then it's kind of guessing what exactly is happening in the next device. Okay. So here then the receiver records the temperature by reading its own thermal sensor and decodes the signal to recover the original data. Okay. So now let's look at example. So you can see like this is a chip. Yeah. So nowadays some of the chips are designed in a way like half of the chip or part of the chip is called secure zone and rest is non-secure zone. Yeah. And nobody wants anything to be transmitted from the secure zone to the non-secure zone. Yeah. So typically this one has separate memory, nobody can see, this one has separate memory. Yeah. But covert channel is a way, or thermal covert channel is a way you can still leak the information. Yeah. So what you can do, maybe you can put an extra program here, yeah, just a software that can increase or decrease the temperature. Yeah, and maybe there is a password store, yeah, in some binary format, and if it's like 0, you can have some temperature. If it is 1, you can have some temperature. Yeah, but how this typically happens? So like let's say at core B at the receiver, you are receiving this kind of temperature. Yeah, there is no change in the temperature, and then it goes up and comes down. There is a change in the temperature, and then there is no change. So no change can be bit 0 and the change can be bit 1. Yeah. So now think there can be a program on this. Yeah. It does nothing for some time, then it does extra load, it increases the temperature and then temperature comes down. Yeah. Then it does nothing. Yeah. So this kind of pattern can be created, and because this one is becoming heated, because they are very close, right? The sensor on this one will have some kind of similar properties. Yeah. So the temperature will fluctuate on that one in the similar way because they are very close to each other. Okay. And then from that information and that fluctuation in the temperature, you can decode something. Yeah. So in the literature, if you will see like these kind of things have been used, and you can decode around like 5 bits per second. Yeah. But if there are sensors that are, you can say, more fine grained, then up to 20 bits per second can be transferred. Yeah. Hope you get the idea. Yeah. So this is just temperature, but you are doing some encoding of the temperature to get the information. Okay.
So what kind of temperature sensors are used in this?
In each laptop, each phone, we have a sensor. Yeah. But this one is assuming you have a sensor here, you have a sensor here as well. Yeah. So these are typical sensors. Yeah, we have in each of them. Okay. Yeah. So I think one of the reason you might have seen like, maybe you have seen some army people or defense people, right? You can see their laptop. It's not like very thin. Yeah, it's very thick laptop. So in the past, it has been like those laptops are doing something. Some people have put some receivers next to it to get its like what kind of power profile it has, what kind of temperature profile it has, what kind of electromagnetic radiations it has, and then from that receiver they can really guess what exactly is happening. Yeah, that is why these are made thick, so that by the time the temperature or power reaches the receiver, its magnitude is very, very low, so you cannot get anything. So this covert leakage has kind of happened in some defense places. That's why people put it so big. Yeah, so no, nothing can be detected. Yeah, okay, good. I don't know, it's a kind of hidden because we changed the slide mode, and this is very active research topic. Yeah. Okay, so now how we can detect that? Yeah, so if something like that happened, yeah, so if you want to stop it, the first thing you have to do is detect it, right? I don't know when we were supposed to stop, have the break, 11, right? Yeah, we can keep going. So detecting, again, there can be many ways. So this is one of the approach that was developed in my group. So what we have, you have the system, right, with many cores, yeah, and this temperature activity is happening on all the cores, yeah. So what you can do, you can collect temperature of all the cores, yeah. So it's like core 1, you have like y-axis temperature, x-axis time, yeah. It's like varying maybe this way, yeah, and it's going up and down on core B like that. So all those temperature values over the time on x-axis for each core, you can do some kind of scanning, and this one is actually called online frequency scanning, yeah. So it's like that temperature you convert into the frequency domain, yeah, and when you convert into frequency domain, so you will find like there is some spike at certain frequency, because that's the kind of frequency at which the temperature is being transmitted. Okay, later on we are going to see some kind of this graph that I said, yeah, it will be more clear. But the main thing is you keep collecting the temperature like every second, every second, every second, every second on each core, transform that into frequency domain, and now again frequency domain is like there is like many frequencies, yeah, and there is amplitude of the signal, and then you keep scanning it like with some window size, and at some window you will find there is high amplitude. So if you find that kind of amplitude, you can potentially say there is an attack or there is information being transferred at that frequency. Okay, so like I said, this is processed with a band pass filter in the frequency domain, and this is like linear scanning band B. So again in the with at different frequency there is different amplitude, so this band pass filter is just shifted from left to right. Okay, there is some center frequency, there is some bandwidth. Okay, there is also some frequency increment, like at what speed this window will slide from left to right. Okay, now like I said, in the frequency domain, if maximum amplitude at certain point is greater than the threshold, you can set again some threshold, yeah, like what should be the amplitude. If it's more than that, that means you can say there is a thermal covered channel. Okay, yeah. Okay, so there are more details in this paper, yeah. So this one is about countermeasure against thermal covered channel attacks. So now here we have seen how it can be detected, yeah. In a bit we will also see like how this can be stopped, yeah. So once you have detected, stopping might be easy, yeah. Detection is the most difficult part. Okay. Okay. I think I have a question now. Let's go there. Okay. So we used in the previous example temperatures, yeah. On each core, every second temperature profile will be transformed into frequency domain, and did this scanning, yeah. So can you think of any other metric or any other parameters apart from temperature that can be used? So this one we get temperature of each core, right? Okay, electromagnetic radiation, yeah, that's good one. You can think of getting electromagnetic radiation of each core. It might be difficult to get, but you need some kind of then sensor on each core, right? Electromagnetic radiation is easy to get for the whole chip, yeah. Again, temperature is also easy to get for the whole chip, but then you need sensors for each of the cores, okay. Change in magnetic field, okay, interesting one. Maybe there is a way, each core has different level of magnetic field, yeah, but I don't know how this this one will work, yeah. If something is executing on some core, well will there be a magnetic field, yeah. So I'm not sure about this one, yeah, if there will be any magnetic field, yeah. I mean, another thing could be, you can simply think of the power, right? What is the power of each core, yeah? So over the time, what is the power level? Because if you look temperature, it's mainly related to power, right? If it's high power, high temperature. So you can also look the power values, okay? There could be lots of other things you may potentially use, yeah? You can also say like, what is maybe the utilization of each core, yeah. So over the time, maybe 90%, 100%, 80%, something like that, yeah. Now if you transform that to frequency domain, it might be you can find like at certain frequency there is high amplitude, yeah, which means there was a point in the processor something drastically happened, yeah, the temperature was increased, right, then you can basically get it. Okay. We have seen this one, we have seen this one. Okay, so now let me tell you, just a second, I think it's loading. Okay, so we developed another system. So now here you can see we are not using temperatures, yeah, we are using IPC values. So it's like instructions per cycle, yeah. So this is very kind of useful metric, yeah. So you can imagine if there is a lot happening, the number of instructions that will be processed per cycle on each core will be a lot, yeah. If less happening, it will be less. Same like temperature, yeah, if it's a lot happening, temperature change will be a lot. So similarly, like to temperature, we used instructions per cycle, and then also we can detect, yeah, okay. Okay, any questions? No? Okay, now let's look the defense, how you can stop it, okay. So here again, this one we are saying it's called like DVFS based traffic blocking, okay. So DVFS means dynamic voltage and frequency scaling, okay. So you basically make the frequency up or down, and in that process you can block it, yeah. So now let's say like this is the signal code that you want to transfer, yeah, with the help of the temperature, like 1010, yeah. You remember, if we want something like this, so we want some profile like this, right? If it is 1, change in the temperature. If it is 0, no change in the temperature. If it is again 1, change in the temperature. If it is 0, no change in the temperature, okay. And this profile we are getting typically with normal frequency label, yeah. Like I said, how you can do, you can put some extra program in the transmitter, and that can just use more of the CPUs or cores, and it can increase, okay. So this is the normal frequency level, yeah. And now let's assume like normal frequency level is somewhere here, yeah, okay. So if you are operating at that normal frequency level, you will get this kind of profile, right. But when you are operating like, let's say here, let's change the normal frequency level to some low level, yeah, that is called dynamic voltage frequency scaling. So you were at normal, but you change it to the low level. Again, you went to normal, but change it to the low level. So you keep changing the frequencies. Yeah. If you keep doing this, you can see like with rise in frequency, there will be typically rise in temperature, but with low, this temperature will not reach until that point. Yeah, it will start dropping much early. So you may get some profile like this. Yeah, because it's fluctuating up and down. So if it's always at up, temperature keeps increasing. Yeah, but now because you are coming at lower frequency, you will get some profile like this. Yeah. So now from here, you can see like it's not easy to get the information in that kind of format. Yeah, because the temperature profile is more or less the flat. Okay. So now in essence, you can think of like you are getting the information with the change in the temperature, right? If you can make the temperature always the same, yeah, that means everybody has to assume it's always all 0 or all 1. Nobody can get any information. Yeah. So with this one, we are doing up and down. Yeah. That's why it's like more flat. Yeah. So it's kind of not easy to deduce the information from this. Okay. So again, with any side channel attack, like temperature, if it's power or anything else, people are getting information from it because it's increasing or decreasing. Yeah. And people are having some decoding mechanisms. So if you can ensure my electronics always runs on the same temperature, same power, no side channel attack can happen. Yeah, and that's what this one is trying to do. Okay. Yeah. So if something like this you are doing, now you can see like you are from normal frequency level, you are coming to low frequency level, right? So now when you go to low frequency level, you are also impacting the performance of the application that will be running on that core. Yeah. So here you get some security, but you have to get some penalty in terms of the performance. Yeah. So that is why we say each defense mechanisms has its trade-off, right? If it's the best defense, it may be heavy, use a lot of process, but then it may impact the performance, yeah, because there is a lot of extra process. Yeah. Also, there could be more energy consumption or something like that. Okay.
So this frequency that we are changing is like the power input to the core.
Yeah. So typically in processors, we change only the frequency. Yeah. This is kind of matched to a power level. Yeah. There are like 20 or 30 frequency levels. You change from one to one, another, and then it says it goes from one power level to another power level. Okay. So this is one defense. Yeah. Changing simply the frequencies. Okay. All right. Any more question on this? Okay. Now let's look some results. Yeah. So like I said, yeah, you have to record temperature over the time. Yeah. This is how it will look like. Yeah. And now this is like basically without DVFS. Yeah. We are not changing the frequency. It's just at the normal operating frequency. If this signal is transformed into frequency domain, it will look something like this. Yeah. It's like some amplitude at different frequencies. Yeah. So remember I said you can use a band pass filter, you can keep scanning, and if at certain frequency the amplitude is more than a threshold, you can say maybe if it's more than 0.02, you can say there is an attack. Yeah. So now this is without DVFS. So with DVFS, you can see the temperature profile will be more zigzag, yeah, or more flat. Yeah. You see like in the previous one, yeah, it was going up down, but at the bottom it was more flat. Okay. So with some real applications on the platform, the temperature became like this, yeah, from this to this one. So similarly, if you transform this one into frequency domain, you get this kind of profile. So you can see here there is no higher amplitude. Yeah. So here you can see like essentially the information is transferred from the source to the destination or the transmitter to the receiver, but this information is not very useful. Yeah. So it's like attack is still happening, but attacker is not getting any useful information. Yeah. So there is a metric called bit error rate. Yeah. So if an attacker is getting all the information perfectly fine, yeah, let's say 100 bits he has to get. If he gets all of them, that means there is no bit error rate. Yeah, he gets all the information. But as a result of this, it might be like he just gets only 10% of the information. Yeah, then bit error rate is like 90%. Yeah, because there's so much error in the data that the attacker gets. So now here, if you see, if there is no DVFS, the bit error rate is very, very low. That means attacker is able to get most of the information or most of the bits. Yeah, maybe out of 100 he can get for like 90 bits correct. But with this one, he is still going to use these decoding mechanisms, but the decoding results will have very high bit error rate. So it's, I think, around 96 or 97%. Yeah, so only 3% bits are correct. So this information is not very useful for the attacker. Yeah. Okay. Okay, so I have again a question, and I think with this one we will also stop for the break. Yeah. Okay, so can you think of other methods and controls than frequency scaling? Yeah. So you saw we did this dynamic voltage and frequency scaling, right, to make the temperature as flat as possible. But can you think of anything else? So the main aim is, like I said, yeah, making this temperature profile as constant as possible. So basically you have to think of like what kind of controls you can have in your processor. Yeah, or you can think from a different angle, what kind of things you can do from software point of view. Yeah, there could be some hardware control that you can change to keep the temperature almost the same always, or you can think from software point of view. Yeah, can there be any help from the software? Okay, so reduce the size of the capacitor in the chip. Okay, I need to think a little bit. So capacitor is typically for storing, right? Storing energy. If you reduce the size, there will be less and less energy, less power. Yeah, could be a way. Yeah, so it's like, you know, in the previous example we saw like there is different power request for different cores. Yeah, so there is different frequency level. So if it's, let's say, all the cores are almost running at very kind of in the very minimal range of frequencies. Yeah, so we changed from normal to low, right? But if that low is not at all available, yeah, because there is no power or no capacitor for it. So if the range is very low, you can't really do anything, right? Maybe even if you change, but temperature profile might be the same. Yeah, so it's like maybe you are running at 2 gigahertz, but if you change to 1.9 gigahertz, maybe it is the same. Yeah, but from 2, so let's say you are going 1 gigahertz, then temperature changes a lot. Yeah, yeah, that's nice idea. So basically you can limit the number of frequency labels or power labels to kind of with some minimum range. Yeah, but you can see with that you can get some security, right? Because nobody can get this information. But then again there will be penalty in terms of energy consumption. Yeah, so why we have so many frequency labels? It's because if not a lot of things are happening on the processor, we want to reduce the frequency to very low level. Yeah, and if something is happening, we want to increase. Yeah, so you can see like by limiting this range maybe to very small, we can get the difference. Basically temperature fluctuations cannot be a lot, but then we cannot save energy. Yeah. So that's what we always say. Yeah? There is always a trade-off. Yeah. You get security, but then you pay in terms of some other metric. Okay. Anything else you can think of? Let's have a break, and we discuss more options. Yeah. After this, in half an hour. Yeah. Okay. Okay, you can hear me? Yeah. Hope you had a good break, yeah? I think it's long, 1.5 hours is too much. So maybe in the next one, like our whole session is 1.5 hours, right? Maybe after 40 minutes something we can have 5 minutes break, yeah? Just so it goes in a relaxed way. Okay, so this was the question we did put before we stopped. Can you think of other methods and controls than frequency scaling to stop the thermal cover channel? Yeah. So I think this one we have discussed. Anything else? What you could think? If not a problem. We are going to cover those things anyway. Yeah. Okay. So let's go to the slide. Okay. No. So one of the method we have developed in our group, and we say it is selective noise based countermeasure. Yeah. So you may think like this is some sort of noise that should be added into the system. Yeah. So you remember, like the main aim was, if there is a temperature profile that is up and down, we want to make it as flat as possible. Yeah, and by doing dynamic voltage frequency scaling, we could achieve that. Yeah, but now you can also think of from a software point of view. Yeah, so you can take a program, that program is not doing anything useful. Yeah. That is why we say it is a noise. Yeah, but you have to select it carefully. Yeah, so that program should not be very light or should not be very heavy. Yeah, so now when temperature profile is again kind of going up and down, and the information is deduced from that, again like I said, main aim is to make this profile as flat as possible. Yeah, so now with this extra program, you can think of using a chip a lot, so you can increase the temperature. Yeah, and at certain points you can remove this program from the processor. So in a way, from a software point of view, it can help you. Yeah, like in my laptop, right? Sometimes you can run a lot of programs, then temperature increase, and sometimes you don't need to run. Yeah, so let's look into this a bit. So this one is like, typically, you remember we said thermal signal can be like this. Yeah, there is a change in the temperature, change in the temperature, change in the temperature, change in the temperature. So this is all bit 1. Yeah, if your thermal signal is like that, from the transmitter or at the receiver, you will know like this is all bit 1. Yeah, easy to get. Now, like I said, what's the aim? Making this as flat as possible. Yeah, so what you can do, when at the transmitter there is a program that is doing this kind of profile, right? So you can add some extra program or extra noise. So when your temperature goes up, yeah, when it starts coming down, you can start that program. So then this temperature will stay the same. Yeah, when again it starts coming down, and when you add, basically you have to also remove at the right time. Yeah, when it again starts coming down, try to add that extra noise. So you may end up getting some profile like this. Yeah, so you can see here now, although this temperature is received at the receiver, but receiver will not get any useful information. So you can say that the bit error rate will be very, very high. Okay, so this is just finding a carefully crafted program that does nothing useful but just disturbs the temperature in a way that makes the information useless for the attacker. Okay, again in this one, like detection can be done in the same way. Yeah, and the defense, like I said, is considering bit 1 represents change in the thermal signal, like going up to down, and bit 0 represents like no change. Yeah, no change in the signal, same like previous one. Yeah, so here, like I said, if bit is 1, yeah, at which it's changed. You can add extra noise to heat the processor, so it will keep the temperature higher, so it's not going down, so attacker is confused basically, yeah. So this is typical software way to do it, and this is the results of this adding this carefully crafted noise. So if you see the temperature signal, yeah, and this is over time, so this one is basically without any noise added, yeah, normal temperature profile, from which attacker is able to get useful information, yeah. Now again, you remember, like I said, temperature goes up, it starts coming down. At this point, you initiate your extra noise. So temperature will not come that down, maybe a little bit down. Again, whenever it tries to come down, you initiate this program. So you will see like more flat profile, okay. So from this one, it's not easy to get the useful information, yeah. So this is like example of one of the experiments, how the results look like, okay. Now this is the result comparison with the DVFS approach. So we saw the DVFS approach, right? You change the frequencies. So this is 4x4 system. So here you can see like the selective noise based has more higher bit error rate, yeah, than the DVFS approach. So the situations basically we considered, these two systems, the selective noise based approach is getting better results, yeah, which simply means it is trying to make the temperature more flat in comparison to the DVFS approach, okay. So there's more detail in this paper. If you want later on, you can look, but with this one I just wanted to give you an idea, like one way is you use hardware controls, but another way is you can use some extra softwares to flatten the temperature, okay. Okay, so now I have a question. So we did DVFS, yeah, and we did noise addition. So can you think of any further ideas? Again, what you want to do, you may want to make the temperature as flat as possible, yeah. Can you think of there is any other way to make it as flat as possible? So we have seen one hardware control, one software way, yeah. Anything else you can think of? Let me put that screen, yeah. So okay, hopefully you will see the screen, yeah, on your phone. No? Okay, before we go next, let me try to give you some example. Yeah, this kind of noise addition is very powerful. I don't know if you have heard about this Malaysian airline, yeah, that got disappeared. So there is a documentary on it. So there is a theory like how it got disappeared. So it said like this was going from to China, right? I think from Singapore or somewhere in Malaysia. So the documentary said it basically had some kind of defense equipment or something, and US didn't want it to reach there. So you know, like these airplanes, they are always communicating at certain frequencies, that with the radar to the base station or all the basically traffic controllers, yeah. So you know, like if it is communicating at certain frequency, so one way to stop that communication is you put a lot of noise at the same frequency, right? Then it's kind of you're jamming everything. like too many requests, then it can't get. So that documentary says there were like 2 fighter jets near to this aeroplane, and they jammed its communication from all the places, and then they kind of hijacked and then took it somewhere. Yeah, this is just a theory. I don't know how much true it is, because that aeroplane is never found. Yeah, and some people say they found some debris or something in Africa, but it's all theories. Yeah, so you can think like noise addition is kind of in a way to stop the attack, but it can be also used to let the system down. Yeah, if there is some communication happening at certain frequency, just jam that channel. Yeah, okay. Okay, so use of gray codes for encoding. I think that's possible. Yeah, need to think a little bit. Okay. Yeah, so I think it's about basically confusing the attacker, right? You use some kind of coding to basically confuse the reviewer, confuse the attacker. Yeah, so could be possible, but need to think more how exactly this can be done. Okay. Okay. So we have seen selective noise, its results. Okay. Sorry. You know, in lots of systems there is a fan, right? These days it's not, but there is another control, another mechanism to control the temperature, right? You know, in this kind of systems, there is a fan. When the temperature becomes very high, it turns on. If it keeps increasing, the speed of the fan keeps increasing. So you can say this is another control that can control the temperature. Yeah. So because it can control the temperature, so you can use the fan speed as well to do the countermeasure. Yeah. Again, run the fan at appropriate speed at appropriate time, so that your temperature profile is as flat as possible. Okay. So one of my PhD students did this work. Let's look how little bit details how exactly it works. Okay. So what it does, it looks 2 things. So one is like T recorded, so it's like the temperature at the previous instance. Yeah, and one is temperature current. So what is the temperature now? What is the temperature previously? Yeah. So this is what we want to know, right? You see, like temperature goes up to down. So if it's high at current, previously it's low, that means there is an information. Yeah. So if it is different, yeah, so basically that's not equal. Yeah, if it's equal, that means there is no information. Yeah. So then you check if the current one is higher than the previous one. Okay. If that is true, so basically you kind of check some range. Yeah, in what range the now it is, and in what range the previous one it is. So we define some range, and if that's the case, basically you increase the fan speed. Yeah, so you see, like the current temperature is higher, right? Now it's higher than the previous. So what you have to do, basically you need to cool it down. Yeah, so you increase the fan speed. Okay. In other case, if it's other way around, if current one is less than the previous one, so basically you can decrease the fan speed to make it even higher. So what is the aim? We always want these 2 temperatures to be close to each other. Yeah, so that attacker cannot get anything. Yeah, so it's like if this one is higher, you increase the speed, so it cools down and reaches close to the previous temperature. Okay. Similarly this one, if this one is lower, you decrease the fan speed, so the temperature can be increased to reach the previous level. Okay. So this is one way, fan speed, and this is the kind of, you know, some trial experiment. Yeah, brute force approach, like my student took different range and find out what will be the appropriate fan speed. for different range, so that the whole temperature can be made as flat as possible. Okay. So this is one way, and these are some results. Okay. So in this one now you can see it has been tried to look all the approaches together. Okay. So this thermal covered channel with DVFS, thermal covered channel with one extra noise. So it's like there is one simple program, yeah, and then thermal covered channel with selective noise. So it's like that extra program is multiplied maybe 3 times, 4 times, but not 100 times. So that is like finding the appropriate level of noise. Okay. And this one is with controlling the fan speed, and there could be different range of the fan speed. Okay. And then here is TCC with DVFS and fan speed. So it's like we are applying both together. Okay. And then here we are applying selective noise and fan speed together. And at the end we are applying all the approach together, yeah, DVFS, selective noise and fan speed. So you can see what is the level of bit error rate. So here is 98%, yeah, that means even though attacker is getting the information, it's only 2% of the information is useful for the attacker, so not very useful, yeah. So this is the basically bit error rate. And we also basically logged the temperature, so you can see what's the temperature level and what is the average power consumption as well. Okay. So you can see here more or less when you apply all of them together, this is the best approach, yeah. But here you have to decide like which one is applied first, which one is applied after that, if you are still not satisfied, like the temperature is not as flat as possible, yeah. Okay. So these are the, you can say, 3 controls in the processors that we can apply. DVFS is widely used in all the processors. Selective noise is just a software, yeah. Fan speed is something else that you can control. Okay, so and if you want to look more details, this is basically published in this conference, and all the experimental setup and everything is provided there. Okay. Okay. Can you think of other covered channels than temperature? I think we have covered this question, yeah. You said there could be power, yeah, there could be something else, there could be timing, yeah, or there could be sound, yeah. So let's go to the next one, yeah. So next one, timing covered channel, yeah. Like I said, sometimes the timing information can be used to transmit real information or sensitive information. So again we have developed one approach, it's called IPD based covered channel. IPD stands for inter-packet delay, yeah. So it's like you send a packet from one place to another. When it is receiving, so it's like how much is the delay between first packet, second packet, third packet, fourth packet. Okay. So we keep transmitting, yeah, and then you calculate like if your received inter-packet delay is greater than some threshold, you can say it's bit 1, but if it is less than the threshold, it's bit 0. Maybe it's not very clear, so let me try to show you with this example. Okay, so here you can see packets are being sent, yeah. So packet 1 is received here, and packet 2 is received after 100 cycles, yeah. Packet 3 again after 10 cycles, and then packet 4 after 100 cycles. So this is how it keeps repeating, yeah. Now imagine at a transmitter that is sending something to the receiver, and if there is some sensitive information at the transmitter, yeah, you can send the packets in a manner like the first packet takes long time and then it will be received late, and the second packet is sent very fast, yeah. So it is received in less time. Okay. So when it's taking long time, you can say there is a bit 1 stored into the transmitter side, and if it is taking less time, you can say it's bit 0, yeah. So this is how you can basically use the timing information to get some sensitive information on the transmitter side. yeah, or on the transmitter core. Okay. So here I would say I can set a threshold like 50 cycles, right? If my packets are received after 50 cycles, I will say bit 1. If it is less than 50 cycles, I will say bit 0. Yeah. As you can see, the timing is very, very useful. Yeah. And the timing attack is actually very popular. It has been done in lots of Intel processors as well. Yeah. So people have tried, like there is some program running, right? In a core, you take another program, you try to measure its time. Yeah. Try another program, try another program. So depending upon the time that other program is taking, you can actually guess what exactly is running in the processor. Okay. Yeah. So this is just very simple example. Yeah. You can use interpacket delay or interpacket receiving time to get the real information from the transmitter side. Okay. Any questions? It's clear? Easy, right? Yeah. Okay, so how it can be detected and how it can be stopped. Yeah. So again, if you remember the temperature one, right? If you want to stop it, you need to make the temperature as flat as possible. If you want to stop the timing one, you want this timing equally the same. Yeah. So all the packets should be received in the same delay. Yeah. The interpacket delay should be the same, right? That's how you can stop. Yeah. Detection, we know it's easy. There could be this thresholding mechanism, like I said. Yeah. If it is received after 50 cycles, it's bit 1. If it is received in less than 50 cycles, it's bit 0. So that thresholding mechanism can be used for detecting, but stopping, you have to just make all these intervals the same. Yeah. So what you can do, basically, you can do some modulations. Yeah. So it's like when it's taking long time, you modulate in a way it takes the same time. Okay. So again, make the side channel information as flat as possible. Yeah. So nobody can get the information from it. Okay. So more details again is in this paper. This is a transaction paper in 2022. So you can look more there. Okay. Yeah. All right. Okay, the next one, inaudible sound covered channel. Yeah. So we saw the temperature, we saw the timing. Yeah. We can also see how the sound label can be used to get sensitive information. Yeah. And how it can be stopped. So, and this is also called an inaudible sound covered channel. Yeah. So it's like we cannot really hear. Yeah. The frequency range is quite different. So it's like, let's say in one of the phone you have some password stored, and then there could be inaudible sound covered channel. Yeah. So it's like sound level for bit 1, maybe it's high, sound level for bit 0 is low, but we cannot hear it. Yeah. And with that, if it reaches some other place, the information can be decoded. Yeah. So again, how you can stop it? The main thing is, again, like I said here, the sound label is high or low, right, for 1 and 0. So you need to make the sound label at the same level so it can be stopped. Yeah. So what you can do, basically you can have some kind of extra mechanisms to really see what is the sound label. Yeah. You need kind of a microphone, right, and that microphone will receive it, and now if it's kind of sensing there is high sound label, low sound label, those kind of things, then it can add some extra sound just to make the overall sound level as flat as possible. Yeah. So this is like kind of jamming. Yeah. So then in that case, receiver will get the information, but it will be like all sound level is same, so he may say every bit is 0 or every bit is 1. Okay. Yeah. So we are not going in much details, but if you want, basically that's in a paper, I will tell you later on. Yeah. So now let's see like how this is exactly basically happens, and how some attackers can bypass this. Okay, so remember, like we said, you take the sound level over the time and translate that into the frequency domain. Yeah, so you will find at certain frequency there is something transmitted, the sound that we cannot hear. So what the jamming will do, basically it's going to add just extra noise at the transmission frequency. Yeah, but attackers can be clever. Yeah, so we proposed some kind of anti-jamming approach, which means how an attacker can bypass this and still get the information. Yeah, so you know what attacker can do, from the transmitter side they can have some agreement like what will be the typical frequency levels. It still cannot be heard by human, but we can keep switching. Yeah, so it's like if signal is being jammed here, it can basically after some time change the frequency at which the information is transmitted. Okay, so it can be modulating the frequency. So in place of transmitting at 18 kilohertz, you can transmit at 21 or 22 kilohertz. Yeah, so you can see like then it cannot be jammed or detected. So this is like a bit of advanced attack. Yeah, similarly you can think of this kind of changing the frequency of transmission in all the approach. Yeah, even in temperature, you remember we transform the time signal into frequency, then we did some scanning, right, and then there was a frequency level. But attackers can be even more clever. They can again they can make some arrangements with the transmitter receiver. They can keep shifting from one to another, and then you are confused. Detection is confused like at which actual frequency really the information is being transmitted. Okay. So this one again more details is available into this paper. Okay. Yeah, so I am just trying to give some kind of high level idea and just telling the main principle how things are happening. Yeah, exact details, equations and everything, they are present in the paper. Okay. Okay, any questions here? Yeah.
So like there was a method which we used to cool down the like course, the fan speed method. So for that we are like not blocking the temperature covert channel, but we are also giving the audible sound na, that can be detected.
So audible sound, I mean, so you mean audible sound with the fan?
Yeah.
It can be, yeah. So it is interesting, yeah. So the noise level of the fan can be used, yeah.
Or we can like use the temperature channel and subtract the sound from the fan and get the signal more proper.
Yes, that's interesting, yeah. It can be done, yeah. We have not explored that, yeah. But some experiments can be done for this, yeah. Okay, good idea, yeah. Yeah, okay, good. But typically this sound covered channel happens in a way that sound level no human can hear. Yeah, so I think the one we hear is like 20 hertz to 20 kilohertz, something like that. Yeah, that is why you see it's like 18 kilohertz. So in inaudible sound range, so nobody hears. Yeah, I think fan one would be like you can still hear. Yeah, but still some attack can be performed. Yeah. Okay, hope you find it interesting. Yeah. There is no real information being used, but all the side informations, yeah, or side channel information to get the real information. Okay, now let's look some more additional interesting attacks. Okay, so these are not like the covert channel, yeah. So whatever has been done in my research group, I wanted to cover some of them, yeah. Okay. So one of them is called aging attack. Yeah, as the name says, you make someone old as fast as possible, so that one can die. Yeah. So same applies to person. Yeah, So if you want to attack a person, don't give them food, yeah, they will die. I mean, they may age faster, yeah, or give them less food, something like that. So aging attack is something like that, yeah. So if I use my phone, there could be a way I make the age of my phone low, yeah. So one of the ways, I mean, there could be many ways, yeah. If you are always using it too much, its age will be anyway less, yeah. But you can make even less by doing something extra, yeah. So we will look into it. So one of the aging attack, I mean, it's also called something like planned obsolescence, yeah. So obsolescence means making it obsolete, yeah, making it kind of outdated, yeah. So again, if something ages too fast, basically it's obsolete, you can't use it anymore, okay. So this is just another term given to basically aging attack, okay. And what exactly planned obsolescence mean? That means things are not aging by its nature, yeah. There is some planning, yeah. That means to deliberately set a product to malfunction within a certain period of time, yeah. It's like someone wants my phone just to stop working within 1 year, okay. So there is a planning, yeah, like within 1 year I want to make this phone not work, okay. So that's it called like planned obsolescence, making it obsolete with a nice planning. And how it is typically done, okay. So let's see, like from a company point of view, yeah, why companies want to do this and how they can do that, yeah. So companies can release new version of products, like new version of the phone, new version of the laptop, and then they set old version products to malfunction, yeah. If they can do that, they are planning you to basically, or they are forcing you to buy basically a new updated product, okay. So again, you are making it age fast just to get some profit, okay. So this is kind of one way to do an attack. It's not about getting any sensitive information, it's not kind of any denial of service, yeah, it's just like getting some profit by doing this. Okay, now I have a question. So quite a few consumer electronics vendors have been reported of engaging in such practice, you know, this planned obsolescence attack. So do you know any of them? Let me share that screen, yeah, I think this one won't work. Not this one, okay, hopefully it will take some time. Okay, now you can see the text box. Have you heard of any companies that have tried to do that? Which means they have tried to make your phone, your laptop to age faster so that you get frustrated, it's very slow or something, and then you are forced to upgrade to a new version. So green screen is used on the smartphones. Nice example, yeah. I mean, if someone makes your screen just green or blank, yeah, so you are forced to basically buy a new product, yeah. Any other, but do you know which company tried that? I mean, the kind of claims that has been done, it's companies will never say it, yeah. But there are reports, if you look, just say planned obsolescence attack by Apple. So there was a time like people felt they were upgrading their phones, and in the previous one they were doing some patches, updates, and that update will have some kind of extra program and that one is going to use one of the components into the processor a lot. Maybe the memory is used a lot, or one of the code is used a lot. If it's used a lot, basically it ages faster, yeah, its temperature rises, and then overall the phone becomes very, very slow, yeah, because if things heat up, they run at lowest frequency, and then you are forced to buy a new product, yeah. So if you will search on internet, you will find like Apple have tried this in the past, okay, but they never claim, but if you search on internet, it is found, okay. Similarly, if you open a company of electronics, you know how to make more money, yeah, you kind of age the products that you sell so people can buy the new ones, yeah. But if you're caught, your reputation is gone, yeah, so you may lose all the money, so careful. Okay, what's happening? Okay, so how this product malfunction is done, yeah. So this can be done by crafting malicious programs, like I said, yeah, like this product updating to the new version, then adding a patch that will use a specific processing element, or this can be also done by inserting hardware backdoors in the form of hardware trojans, yeah. Again, there could be a specific component, after some time it starts using some other component too much, and then whole system becomes slow, or whole system dies basically, yeah. So this can be exploited to accelerate aging of key components, okay. So a program or some extra hardware circuit, okay. And here a hotspot node is a typical target. So typically the component in the processor that is used a lot, you want to use even that more, so that it becomes slow and it ages faster and whole system is basically shut down. Now let's look at an example of network on chip aging failure, okay. So network on chip, you know, we saw this 3x3, right. So each of the cores are connected by a router, and then routers are connected with some links. So that thing is the router and the links, they are called network on chip, okay. So here if you look, if in this network on chip, so these are processing elements connected by the router. If one of the processing element fails, then you can shift the workload of this to something else, yeah. So there is, because there is core redundancy, so that's not a problem. But if one of the router fails, imagine now no communication can happen through it, okay. So this is more serious, so whole chip fails. So some companies may try to do that, like just making one of the centralized router fail, so whole system comes to a stop, okay. And what is manufacturer's preference to do this? So as soon as the warranty expires, they want to do it, yeah. So after that you cannot go to their warranty center, yeah, like my phone has stopped working, like warranty is done. So you prefer basically replacing to the new one, okay. So that's typically the time the vendors want to do it, and this is all towards maximizing the profit, okay. How the profit model can be developed, yeah. Now let's say there is a series of phones, yeah, like maybe Apple or Samsung, yeah. There's a lot of I series, yeah, 14, 15. So if they are coming with their ith version, that is the next version of the device, yeah, let's say iPhone 15. So what will be their profit? So it's like how much they have produced, all the quantities, so the price for each minus the cost for each, yeah, and how many they have produced, yeah. So this will be the total basically profit, okay. And this SI is basically the number of sold prices for this ith version, okay. Now if you are planning a planned obsolescence attack, you have to basically make sure the new version is sold as much as possible, yeah. So there could be some equation like that, yeah. So let's say how many new devices of the new version are sold. So there could be some new customers, yeah, that is S0 here, and there could be the previous customers like that are in maybe I minus 1 version, yeah. If it's I15 is released, then who are in the 14th version, who are in the 13th version, and then what is the probability of them to change the phone, okay. So this is how companies can estimate how many of the new version device they can sell, yeah, okay. So just this is kind of a profit model we have developed, okay. Now let's look one of the aging attack algorithm that we have developed. So again, how it works, if you remember I said if you look over the time, there is a warranty time, right. So this one is like years, yeah, this is like 3 years, and if the warranty is like 2 years, so just after 2 years you want your device to age fast so that consumers are forced to replace. So on the vertical axis, this is a value called change in the threshold voltage, okay. So for any electronics are made of transistors, yeah. So these transistors over the time there is a change in the threshold voltage and it keeps increasing, okay. So if you are running in a normal condition your device, yeah, so it's like it will start here, yeah, the red line, yeah. So if like after 1 year the change in threshold voltage might be like 8, yeah, after some more time it will keep changing, okay. So in the normal condition you can see reaching it to 10 might take like 3 or 4 years, yeah, and when the change in threshold voltage reaches 10, we are assuming like this is the failure threshold point, okay. After that the device may become very, very slow, it's kind of useless, okay. So in a normal condition that will happen, yeah, but if you want to aggressively age this device, you can try to reach 10 as quickly as possible, right. So there's something like aggressive aging, yeah. From the very beginning you try to use it too much and then you will reach this change in the threshold voltage maybe just in 8 months, yeah, and after that the device becomes useless, okay. But what can be the nice planning, yeah, planning could be in a way until 2 years you don't do much, yeah, you try to reach there, but just after 2 years you start it aging, yeah, in maybe in 2 years 1 month your device is gone and then you are forced to buy it new one, okay. So this is basically, this is how planned obsolescence is done, okay. So reaching the failure point at the right time as soon as the warranty expires, okay, yeah. So this is how, I mean, how this can be done in a kind of a network on chip environment, yeah. We looked network on chip, you saw, right. So with each router we can attach an entity that can have 2 components. One is trigger, that is going to basically trigger where that router should be used more, that means accelerate, whether that should be used less, so decelerate, okay. And this is kind of a routing computation stage, yeah, this is called like routing computation, like how the packets are going to flow, okay. So here this one basically can be exploited to accelerate the aging just after the warranty period, okay. Similarly, like before the warranty period, companies may try to kind of decelerate so that it reaches the thresholding point just near the warranty point, yeah, not much faster, okay. So here, like if you want to accelerate, this is how you can do, yeah. Let's say there is a source, there is a destination, you are sending some packets. If you remember I said there is a like a hotspot node, yeah, that has to be used a lot. So they can route a lot of packet from this, yeah, from all the source to this. So this particular component or this particular router can fail, and then most of the chip become useless. Okay. So this is how you can accelerate. Similarly, you can decelerate, but you want to do it before the warranty period. Yeah. So here, let's see if that particular router is being used a lot. So if it is less than 2 years, you can try to use another path. Yeah, something called like XY routing. So that hotspot is not used a lot. Yeah. So this is like one way to do the edging attack in a many core system that is based on the network on chip. Yeah. Okay. So this is a question. Can you think of any other way to do the edging attack? So in the previous one, we just tried to use the hotspot node, hotspot router more and more, right? And this one is basically just setting the hotspot node as a temporary destination, so it can edge faster. Can you think of anything else? Let me do that screen. Hopefully you see the screen. So any other way to do the edging attack in the context of this network on chip based processors, okay? I mean, just you can type your thoughts, yeah, don't worry if it's wrong or right, yeah. I have just thought only one, but I wanted to check if you have thought something different than the one I have thought. Increasing the power input to chip after warranty so that it may heat up fast. Interesting. I mean, that's one way, but typically you have to use the hotspot more and more. Yeah. So even if you are increasing the input power, somehow you have to divert more power to this hotspot node. Yeah. So that's one way. Using very fragile routers can be, but typically when you design the system, you make it the same, right? Yeah. Lower quality of camera. Okay. I think it's all about quality, yeah. Anything that require high computation and has no and little workaround could be prone to aging. Yeah, that's true. Yeah, that's what we are doing here, right? We are sending more and more packets. Recall this hardware Trojan thing, yeah? What exactly it was doing. So hardware Trojans, like, it's related to basically the first point, yeah? You can say increase the power level, but maybe you can have a hardware Trojan in one of the routers, and when the power requests are going to the global manager, this one can always request more and more power, yeah, and it can heat it up and then can let the whole system down. Yeah, that's one way. Okay, you can hardware Trojans can be used. Okay, good. Okay, sorry, not this one. I need to go that slide. Just a second. Okay. So, I mean, this for this aging attack specifically, yeah. If you look this paper, that is about emergent design challenges for embedded systems and paths forward. So if you look in the security section, yeah, or reliability section, you can find like how this aging attack is done, yeah. So more details are into this paper, okay. Okay. So next one, again that has been done in my group. We are going to look in vehicle network attacks and countermeasures, okay. So you know, like the vehicles, like the cars that we used, there is a network inside it, yeah, but that network can be attacked, and then how that attack can be stopped. So this one we are going to cover maybe after 5 minutes break, yeah, like I said, it'd be good to relax a little bit, okay, just 5 minutes of break, then we start, okay. And if anyone has any questions in the meantime on the aging attack or the one previous we did lots of covert channel attacks, feel free to ask, yeah. Okay, 5 minutes. controls, you can say, yeah, and these controls are connected by some network. Okay, so we will come to it how exactly they are connected. Yeah, so if you look this kind of contemporary vehicles or car, they have several features, and these are basically powered by some electronic systems. Yeah, and these features help the drivers and the passengers in terms of convenience or something they want to do. Okay, so there is a lot of electronic systems. Okay, and these electronic systems are realized into something called electronic control units. Okay, so if you look at typical car, modern car, you will find like 100 or 200 electronic control units, in which lots of tasks are happening during driving, depending upon what exactly you are doing in the car. Okay, and these ECUs are connected by a network that is called control area network. Yeah, or you might have heard CAN bus. Yeah, this is very popular in vehicle networks. Okay, and this is sort of the de facto standard for communication among electronic control units in the vehicles. Okay, so CAN is basically connecting all the electronic control units. Okay, now let's look a bit more detail about this network. Okay, so this network connects to external systems through connected and autonomous vehicle technologies. Okay, so anything you want to do in the car, like you want to play maybe some song or something, there will be a controller for it. Okay, that will facilitate that process. Okay, but the problem with this CAN is it does not provide confidentiality, authentication or access control. So it has no kind of security proof mechanisms, and that is why it allows attackers to access the CAN bus, and attackers can inject some packets. Yeah, so it's like they can throw something into some electronic control units, and then whatever the car was supposed to perform, it will do something else. Okay, and with this kind of approach, attackers can target some essential functions, yeah, such as emergency braking. Yeah, you want to apply, but then that particular electronic control unit that is supporting the brake, maybe it's malfunctioned. Yeah, then basically brake will not be applied. Okay, it can be acceleration as well. Yeah, so like you are trying to accelerate your car, but the corresponding electronic control unit has been attacked, or like the real information in it has been changed because there is no proper authentication or confidentiality. Okay, and it could be steering control. Yeah, like you are going on a car, it's like straight, but you have to turn, but if someone attacks, maybe you cannot turn the car and then you crash. Okay, so a lot of these things are possible. So now how the attack on the CAN bus can be done. Okay, let's look a bit. So a potential attacker basically may exploit some external interfaces. Okay, something called like OBD2 diagnostic port, or some telematics unit, or in-vehicle infotainment system. Okay, and they can launch some attack on a real car from there. So let's say this is a car, right, and there are a lot of electronic control units into it. So the CAN bus in the car can be connected with some external interface, and these can be the external interfaces. Okay, so with OBD2 port, an attacker basically can send some message into some electronic control unit that might be compromised, and this one, like I said, maybe it's a steering control, or it's a brake, or it's acceleration. So those things are not going to happen. Okay, so this is how the attack can be done. And what exactly it will lead to? It will be basically denial of service and malfunction and lot of other things. Yeah, so basically not doing what exactly it should be doing. Now how the CAN bus frame looks. Yeah, because you want to do the attack, which means you want to change something into the frame. Yeah, which means this frames are going into different electronic control units, right? So you want to change the value. So the frame looks something like that. It has some bit for a start of frame, this CAN ID, this is something called like data length code, yeah, and this data payload and some checking, acknowledgement, and end of frame, okay. So here what exactly you can do, you can change the CAN ID and data payload to trigger an attack, okay, because there are a lot of CAN messages going from one controller to another. So for a particular CAN ID that might be going into some electronic control unit, there is some payload as well going with it, right, to do the braking or to do the acceleration. And if you can change that payload, then it will not do acceleration, it might do something else, okay. So this is how basically you can change the payload and CAN ID to do the attack. So this is a kind of sample data for Tesla Model 3, yeah, how exactly the data looks in Tesla Model 3. So you can see there are a lot of CAN IDs, and this is data length code, which means how many bytes are going to be used for the whole data, yeah. So you can see like data 0 to data 7, there are some data stored, okay. This is the sample data, yeah, there are like millions of CAN IDs flowing, yeah, because there are so many things happening in the car. So this is an example, but here this one is a real data for Tesla Model 3. So you can see like this is some index, like from the software we extract the data, this is the time, this is the CAN ID, and the data length code is not 8 always, yeah, which means how many this payload are there, okay. So if it's like 7, there will be 7 payloads, last one will be empty, okay. If there is 2, only 2 payloads, rest of them will be empty. So this is from Tesla Model 3, yeah. And now to do different things, there is different payload, yeah. If you can change whatever is car supposed to do, it will not do that. So now let's look at real attack, yeah. So this is changing the CAN ID and payload, trigger the lighting, yeah. So it's like car is standing, but for the CAN bus you can connect with some ODB port, and through the ODB port for a particular CAN ID you can change the payload and it will just trigger the lighting of the car, whereas you are not doing from the real control, okay. So let's look this video. I think I need to increase the volume, yeah. Hopefully.
Here I'm showing to you how we can attack the car through the CAN bus.
So this is done by one of the master's student, yeah. So this is
And here is the device we used to
inside
record
Tesla
the
Model
CAN
3,
message
yeah.
from the car. And here it is the OBD port we used.
So in the car this is available, yeah. You can connect.
And this one is the cabin we used to connect it with between this device and the car. And we plug it in the OBD port. And here is the USB we used to connect between the laptop and this device. And here is the software we use to read the message from the canvas. And now we can see there are so many messages.
I pasted some of it, yeah, in the slide
If we try
before.
to do some attacks, I can control many things. And now I show you I can choose the light. And here is the message which can control the light from the canvas. And if I press the send button, the light will shine. And let me show you. Yeah.
So you see, like for a particular CAN ID, you change the payload and then it turns on the light, yeah. So it's
And
kind
when I
of,
send it, when I stop it, and that's all.
so there is no proper way to find out what is exactly the payload for different controls. So this is like trial approach, yeah. We found for this is like the payload for the light to turn on by sending the through the CAN network, yeah, for particular CAN ID, because that ID is going into that electronic control unit that is connected with the light, yeah. So now imagine if you can find the payload that controls the steering, yeah, you can maybe freeze the steering, yeah, or you try to accelerate the car, but you pay, I mean, when you accelerate the car, the payload will change, right? But you may put some payload always constantly, and then it will not accelerate, it will not move, yeah. And the reason we could do this CAN is no authentication or something in the car, okay. So it's very easy. There is a port, you connect, and then you can do it, yeah. So with this one,
Here I'm showing to you how we
just-
can attack the car through the camera.
so we have also performed attacks like opening the back trunk, yeah. So you're like standing, but you can open the boot just by changing the payload, and also turning indicator, yeah. You're not doing anything, like not the control, but rather just by this changing the payload, okay. I think student is still trying to figure out what can be the payload, maybe to freeze the steering or something, yeah. It's very dangerous, so that is why you see this car, it's never moving when things are being done. And also there is a lock, it's like in a compound, yeah. If something goes wrong, maybe the payload you put, maybe it starts moving, right, or accelerates. So it's in a very closed compound, anything crashes or something, it's not a problem, yeah. So the vehicles are really insecure, yeah. Imagine like someone getting that kind of access from internet, and then he can just try changing the payload, and lots of things are going wrong in your car, okay.
Yeah, then integrating AI with that.
Yeah. So yeah, so cars are very insecure, okay. And with more connectivity, nowadays cars are connected, right? I don't know if you know, like there are some cars like now connected with cloud. If you're driving, they ask like to do some updates over the cloud. Like you will be scared, like you're driving and some updates are happening. And when that update is happening, imagine some attacker getting access to that. Yeah. Okay, so now because CAN is so sensitive, I think some automotive companies, like one in US, General Motors, they are coming with a different infrastructure for communicating that can be more secure. Yeah. But there is again no authentication or confidentiality. Yeah. That just kind of more secure it can be, okay. Yeah, I think they're trying something like compartmentalize it. So it's like one network for critical systems, one network for infotainment system, one for maybe driver assistant, something like that. So there is never a kind of only one bus, CAN bus, that is always talking. So just to have different kind of messages in different sections, yeah. Okay. Okay, I think this is the question now. How such attacks can be mitigated? So how we can stop these in the car? Can you think of some? Let me put that slide. Any ideas you can think how this changing the payload for a particular CAN ID can be avoided? So again, this is very active research. Yeah, people who work in automotive systems, they do a lot. Encrypting, good idea. But like I said, in the CAN bus, there is no authentication or encryption. Maybe it's because it's already very heavily loaded system. Yeah, there are so many messages are flowing from one to another. Yeah, when the car is running, maybe there are like thousands of messages. So if you encrypt, these are longer messages. Yeah, so it can basically impact the performance. Yeah, I think one of the reasons is car is like a critical system. Yeah, like I said, when you there are some critical parts. Yeah, apply the brake, it should be applied immediately. You turn the steering, it should be done immediately. Yeah, if you encrypt, it may take some time to respond. That's the reason, like, they don't want to do a lot of these things. Yeah. Okay. So don't worry, next slide is about that. So let's go and check. But in another one, yeah. This one. All right. Okay, so to detect and mitigate CAN bus network attacks, we can have something called an intrusion detection system. Yeah, this is very popular again. Yeah, so you remember this is how the attackers with one of the external kind of interface they can send the message. Yeah, so in one of the electronic control units you can have some sort of monitoring. Yeah, what exactly is the payload coming. Yeah, so all the payload pass through it and then it goes to the relevant control units. Yeah, so if you find out like this kind of payload has never been observed, you can do some alert. Yeah, so I mean it's still not stopping, or that payload you may stop sending to the electronic control unit, it is going. Yeah, so lots of people have developed this kind of systems like intrusion detection system. So what it is going to do, basically it's just going to filter out malicious traffic or malicious payload, yeah, that attacker tries to send to the CAN system, okay, and generating the alert system. Okay, so that's just high level overview. Now I wanted to kind of introduce some kind of methods that has been proposed in the literature already. So these are like the two intrusion detection system methods. Yeah, so one is based on deep convolutional neural network. So again, you may feel like it's trying to find a pattern that has not been observed, yeah, or it's deviating too much from already existing patterns of the payload. So a CNN is used for that. That is in this paper, and there is another approach, kind of multi-layer perception approach, again CNN based, to kind of just detect and stop that. Okay, so it's just basically you need some kind of intrusion detection system. Everything that comes in the car, in the CAN bus, has to be checked there. Yeah, and if it is deviating too much from already seen workload, then you somehow stop it. Okay, yeah, but to my knowledge, in the real cars there is nothing like that. Yeah, so you can still attack. That is why we could attack this Tesla Model 3. Yeah. So now a key message for modern cars. So now you can see modern cars have increasing features, right? So with increasing features, there will be trade-off between resource requirements. Yeah, they're like limited electronic control units. You want to do more in that. So the complexity is increasing. Yeah, and we want to extend the functionality as well. Yeah, so there is kind of extendability issues, and with all these, there is another issue called like certifiability. Yeah, so in a car, if any new component is put, it's not like the system we use. Yeah, there is always a certification. Yeah, upgrade something, it has to be certified, because it can create, it can kill someone. Yeah, so such kind of system need that kind of thing. So again, with all the increasing functionalities that we are getting in the car, engineers have to solve this kind of trade-off. Yeah, confidentiality, complexity, extendability. Okay, good. I think we will stop here. Yeah, in the afternoon we are going to look some differences that is based on authentication. Yeah, authentication you know very well. Yeah, we always do it. So we are going to look like how that can be done, or even if you do some authentication, how that can be bypassed. Yeah, that's not sufficient. Attackers are clever enough to kind of bypass that, and then how we can stop that. Okay, yeah, let's look in the last 1 hour in the afternoon. Okay, I think we have 1 hour. Yeah, 2 to 3. So we are changing the structure a little bit. Yeah, I said in the morning. Yeah, so lecture 7 was about design methodologies for sustainability, and then there was something about security. So I said we will cover everything about security today, tomorrow sustainability, and then combining together. Okay, yeah, okay. So this one we will look in the afternoon, and this is a work basically done with one of the companies in UK. It's called British Telecom. Yeah, you might have heard. It's called BT Research. So I have a PhD student, like industrial PhD student. He has done this work. Yeah. Okay, have a good lunch and see you at 2. Okay. security, yeah, cyber security. So the next one we said we will look authentication based defenses, yeah. As the name says, you need to do some authentication, yeah, to basically log in into some system. So let's look first this. So typically what we do is something like static authentication, yeah. So static means like it's done just only one time, yeah, at the very beginning. Once you log in into the system, then there is no authentication, okay. So in a typical scenario, a user sends a request and then there is some server where the authentication takes place, and if your credentials are fine, it will kind of return a green response, you will be able to successfully log in. If not, there will be like bad response, yeah. And these authentications use this kind of protocols, yeah, okay. So I have put a question. So what do you think about this kind of static authentication? Is this enough to secure a system or not? If not, then why do you think it's not? Okay, let's go that slide. Okay, if you open the same web page, the question will change, yeah. Let me see for me. Yeah. So this is typical way we log in into any system, right? No, that authentication token can be used by hackers also to gain access to user profile. Yes, it can be. So basically you may say login credentials can be used by someone else, right?
It's more like cookies.
Yeah, and we need to verify the sender. That's important one. We need to typically verify the sender, yeah. Even if some authentication has happened, there could be some extra mechanisms to verify, yeah. Once the passwords are leaked, then anonymous person can access the profile. Correct? Yeah. Okay, so let's look like I have my own logic, yeah. For me, there are lots of situations this kind of static authentication is not enough, yeah, and we will see like why it is not enough, and then we will see what can be done to fix that, okay. So we go here. I think it takes some time to load. So there are some issues with this kind of authentication, yeah. So I would say in summary, these are inefficient in dynamic and high risk environments. Okay, let's look what can be the potential issues in this dynamic and high risk environment. So one of the issues can be spoofing, yeah. So spoofing is like someone is trying to mimic your behavior, okay. So what attackers can do, they exploit vulnerabilities by mimicking the hardware and software configurations of legitimate device to gain unauthorized access. So even though you have authenticated, yeah, there could be another attacker, he's trying to use the same configuration. He doesn't need to do authentication. He's trying to mimic the same behavior of the device and then trying to gain access in the network, yeah. Some example could be the IP address, yeah. So it's like each device has an IP address, right, when it's connected, but someone else can assign some IP address to his own device, the same one, and then he can try to come in the network. Yeah. Similarly, it can be done with the MAC address. Okay. So in this kind of scenarios, you can see like even though one-time authentication is done, but then with the system behavior with that authentication can be copied or spoofed, and then someone else can log in the same network, yeah, pretending like that is also a legit person. Okay. Another thing could be cloning. So it's like copying, yeah, and trying to clone to other device as well. So more or less like spoofing, yeah. Okay. The third one can be spill, yeah, as the name says, spill, yeah, too many things, yeah, throwing so many things, yeah. So someone can create multiple fake identities in the network, yeah. So for a real authentic device, someone can try maybe same IP for 10 device, and he can try to log into in the network, yeah. So although you have done the static authentication, but someone may be able to come in the network. Okay. Someone can also do some physical tampering, yeah. So they can remove and add something. For example, they can connect some jumper or something to connect with some external device. Okay. So I would say these are some of the problems with static authentication. Okay. So I have a question here. So like those spoofing, spilling, cloning, yeah, those things, how do you think that can be fixed? So in summary, how static authentication issues can be addressed? What do you think? We go to that slide, yeah. So in essence, you have to stop this spoofing, right? You have to stop cloning. You have to stop spill. How that thing can be done? We need to verify the authenticity of each of the transactions. That's a good example, yeah. So it's like whenever any user is trying to get access or to some network, you can try to authenticate for each transaction, yeah, but then you may end up authenticating maybe too much, yeah. Your user might be so irritated, right? And I think even if you use multi-factor authentication, this issue will still be there, yeah, because someone is just cloning the device after authentication has been done. There could be session tokens, yeah, that's nice idea, but it's can be difficult to find out like how long you want the session, right? 10 minutes, 1 hour, something like that. So by using dynamic authentication or using multiple authentication layers for critical tasks like for transaction, I think you are getting closer. You need some kind of dynamic authentication, yeah. So dynamic can also mean like continuous authentication, yeah, but you cannot ask a user to keep entering the password all the time whenever he asks for something, yeah. So there are some ways how we can do dynamic authentication. Okay, let's look. Okay, so the fix to those things is continuous authentication, or you can say dynamic authentication, yeah. So we recently have published a paper, it's called continuous device to device authentication exploiting crystal oscillator impurities, yeah. So in each processor there is a crystal oscillator, right, that's basically making the clock. There is some impurity into that, so we can use that feature to do continuous device to device authentication, yeah. We will come to that how exactly this can be done. Okay. So this is the high level overview of the continuous device to device authentication framework. So it has basically two steps. Yeah, one is identity establishment. So it's like, let's say there is a network, a device wants to connect in the network. So first we need to find its identity, or you can say first we need to find its fingerprint by using some characteristics or features of the device. Yeah, like I said, crystal oscillator impurities, that's one of the features you can use. And after that is done, you can keep doing continuous authentication by storing the identity in the server. Yeah, so let's go a bit more details here. Yeah, so how you can do this identity establishment phase? So it's like each device is kind of, you have put login password. Yeah, after that you can extract some features of the device, and you can do some feature processing, and you can generate some fingerprint. So this will be like very unique to that device. Yeah, and it typically leverages natural hardware imperfections. Yeah, and one of them is crystal oscillator impurities. So how this is done, how we have done it, it's like for each device basically you kind of put a nope instructions, it's not doing anything, and then for crystal oscillator impurities you just capture CPU cycle count. Yeah, and then you store it for some time, then you reboot the device, and then you store it again, you reboot the device, you store it again for some time. Yeah, and then overall some executions you then come up with some fingerprint that will be very unique to that device. Okay, now in continuous authentication phase, basically this continuously track the change in the device behavior. So like when over the time it's tracking the device behavior change, and it applies dynamic authentication policies. So basically it kind of decides some timeline when the device has to be authenticated with the fingerprint that is already generated. Yeah, it's like a static authentication is done. Yeah, after that you store the fingerprint. Yeah, and over some period, depending upon how critical the application is, we will come to that, this continuous authentication over the server can take place. Okay, so this, like I said, follows a bit of client server model. Yeah, each device is a client, and where the fingerprint of the device is stored is a server. So like I said, fingerprint is stored at the server, a client device needs to be continuously authenticated, and the server end performs the authentication, which can be on the server or that can be on a deployed router as well. Yeah, let's say in a home there are a lot of devices, right? So all the fingerprint of each device can be stored on the router. So if someone else tries to basically clone your device or spoof your device identity, and if there is this kind of continuous authentication, you will know, like even though they know the login and password, but the feature will be different for their device. Yeah, like I said, each device has all different features. Okay, the reason is there is some imperfections when they are manufactured, so that imperfection can be used. This is fingerprint of this one, this is fingerprint of that one. Okay. Okay, so now I have a question. When do you think this continuous device to device authentication framework won't work? There could be some situations it's not going to work. Yeah, I would say we already have seen it. Yeah, so if someone gets your ID and password, yeah, and then basically then this is no point. Yeah, they can always log in. Okay, so that's one of the situations. So first you ensure ID and password, that should not go anywhere. This one is like if someone authenticated, someone tries to clone your device, same identity tries to create. then basically it can stop. But if your password is gone, everybody can do it. Yeah, okay, good. Let's see, it stops here. Okay, so like I said, there's something called like device authentication timeline. Yeah, so when do you decide how frequently you need to authenticate, or like how late you want to authenticate? So let's look the first one. So here you can say for one device, this blue line is something called like identity establishment. Yeah, it's like fingerprint generation and storing in the server. Yeah, and initially you do some kind of continuous authentication. Yeah, but if your device is low risk, yeah, you don't need to do authentication so frequently. You can do at kind of some higher interval, yeah, maybe every 10 minutes or something. But if the device is high risk, you always want to do at more frequent intervals. Yeah, and how this interval is determined, so we developed something called like device authentication score. So it's kind of says how authentic the device is, and based on that how frequent or how less frequent the device needs to be authenticated. I think we are not going into the details of this formula, it's in the paper, I will point out. So it's like if device authentication is more than 80%, it is a lower security risk, which means you don't need to authenticate so frequently. Okay, so which means high or device authentication score indicates there is huge confidence, there is no problem. Yeah, so score is high. Similarly, if score decreases, it becomes medium security risk, and in this range we have classified that this is high security risk. And if your device authentication score is less than 50%, which means there is kind of no confidence whether it should be further authenticated or not, because you assume this is some attacker. Yeah, so in that case you can say unauthorized. Yeah, you can basically stop the access of that particular device. Yeah, for example here. Yeah, so that device can be eliminated from the network. Okay, so this is kind of continuous device authentication timeline. And these are some evaluation results. So here the first column shows devices. So we have device 0 to device 10. So these, all of these are Raspberry Pi board, yeah, you might have used. And then the second column shows precision of change. So it's like the fingerprint is stored, yeah, and when it is monitored later on, how much is changed over the time, yeah. So you can see like if the change is low, the device authentication score will be high, right, which means it doesn't need to be authenticated so frequently, so the risk will be low. Yeah, but if this change is a lot, that means it's varying too much from the fingerprint that is stored, right. So you can see the device authentication score is very low. In that case, you can assume like you don't need to give access to that device in the network. You can say unauthenticate. Yeah, okay. So kind of here you see we do not have lots of device, but recently the student is trying a lot of like 50 of the Raspberry Pis, and kind of so that this range can be a lot. Yeah, but we have seen like low and high score device as well. Yeah, so here you can see this precision changes has some values. Yeah, kind of 5.2, and then device authentication score is around 52. So according to the previous bracket criteria, it falls into high risk. Yeah, so it needs more frequent authentication. So it can also be over the time the same device can go into different categories. Yeah, maybe at the beginning it was 0.02, this precision change in the precision, but after some time it can become 3.08. So depending upon how much the feature of the device is deviating from the stored fingerprint, you can decide how frequent or how less frequent this continuous authentication has to be done. So it's not always the same for one particular device. It keeps changing depending upon the precision of change. Okay? Any questions? No? So for more details, you can look into this paper. I think this was recently presented. I think I already have told this is a work with one of the company who produces routers in the UK. So they have like a huge network. So it's British Telecom. So they want this kind of techniques because in their router there could be lots of devices that are trying to access, but sometimes there could be attack. So just to make sure in their customers' router they are not unauthenticated, or not attackers accessing that. Yeah. Okay. I don't know when this is going to come into the product, but it can be at some point. Yeah. So it's like in your home there is a router, there is a lot of devices connected to the router, right? Then for each device at the beginning you do multiple restart, yeah, and in these restarts you collect a feature. In this one I said it was cycle count, yeah, and then over the 5 or 6 restarts you make a fingerprint, you store that in the router. So if someone else tries to clone your device, their fingerprint will be different, and if it's deviating too much, you can kind of say, the router can alert you like there is unauthorized access or unauthorized addition of some device in the router. So this way unauthorized access can be prevented. Okay, any questions on that? No? But you can see this is interesting, yeah. Attackers have lots of ways to clone your device, or you can say copy the features of the hardware and software and then mimicking like it's actual, yeah. It's kind of like social engineering, yeah. Someone tries to call you from maybe bank or something, so kind of, yeah, they try to clone not the person, rather the device. Okay. Yeah. So the next one I want to cover is work by another PhD student, is video manipulation attack in IoT environments. So as the name says, there is some video, yeah, it's playing, and there is some manipulation of that to do the attack. Okay. So let's look for some motivation, yeah. So if you look lots of IoT systems like flood monitoring, they rely on real-time video feeds, yeah. So there are a lot of countries, I think this figure is, I don't know, not from India, so this student is from Nigeria. They have a lot of flood problems, so there are a lot of cameras that are getting streams and sending to the server, yeah. So like flood monitoring basically relies on videos, yeah, and these feeds are vulnerable to manipulation attacks. So what does it mean? When the video is going from this point to the server, someone can do something in the middle, or someone can do something at the storage point, and then it's actually not that video, rather some other video, yeah. And this can be done in these ways, yeah, like replay. Replay is something like you store another video in the device, but you replace it with the previous one, and it's just playing the same video again. Okay. Frame injection and hijacking, I think I will come to that in a bit, yeah, what exactly are those. So one question here, where else video manipulation attacks may happen? So we saw IoT environment, yeah, like the flood monitoring. Where else do you think this kind of video manipulation attacks can happen? Okay, let me see this one. Okay. Banks. Okay, I think I was thinking that example, Are you thinking to kind of rob the bank? I mean, you might have seen some movies, right? People just, maybe these movies, Doom or something, they were all like that, right? They go hack inside the physical premises, upload some video, it's not the current but the previous one, yeah? That is exactly replay attack, yeah? They play something else repeatedly and it's not the current but something else, yeah? So of course, if you want to rob the bank, you can do that, yeah? I think lots of movies, yeah, lots of movies that. Hotels, yeah, can be done. I think deepfakes is a nice example, yeah? So it's like very similar video, maybe the feed is for flood monitoring, but you may say like there's no flood, yeah? So it is kind of, it can cause some kind of disastrous situations, okay? Online streaming, of course, like always you can replace some kind of unwanted contents, yeah, with something that you want, okay? But I think best example is banks, yeah? You can go like feed something that it's like yesterday's and then in background people can loot it, yeah? Good. So now you know where else video manipulation attacks may happen. Okay, hopefully this will move slowly. Okay, so now we talked a little bit about replay. So now let's look at additional attacks and detection, yeah? So replay, like I said, you take some pre-recorded video and replace with the real-time feed, yeah? Just to, again, some previous video. There could be frame injection attack. So it inserts altered frames periodically. So it's like that, like typically in camera, there are like 15 or 20 frames coming, yeah? From time to time, you replace with something else, yeah? So it might be there was a moment that there was critical information, but then you confuse the person who is really kind of monitoring the video, okay? Another one is the stream hijack. So it's like something is running, yeah? And after some point, you take the control and you replace the content with something else, yeah? But then it's again whole new video or something like that, okay? So it's after a certain point you replace it. But what are the challenges with these attacks? So basically these attacks modify video either in bulk or at fixed intervals. So you can see, yeah, in the replay it's like everything is replaced, right? In this one also everything is replaced at one point. Because of that, it's very often easy to detect it, yeah, because there's huge change. So anyone can monitor, yeah, any human can monitor, or maybe there is some kind of monitoring in the processor that can also detect it, okay? So these attacks are disruptive, yeah, but they can be detected easily, okay? Okay. So this student proposed a more smarter attack. So like I said, if you want to be the security expert, be first attacker, yeah? Then you can develop the best defense. So I asked him to develop the attack methods first. So he named the approach called like dynamic frame alteration. So again, it's a bit similar to the previous one, the last one, where you alter the frames after some point, but in that one it's kind of done very abruptly. It's not identifying any nice moment, yeah? But in here, when some kind of video is running, he has a stored video, he tries to find out the right time. So when like the contents of this one and content of the stored one are quite similar, or there are a lot of similarities or feature similarities, then you replace. Then it's not easy to detect, okay? So that's how it happens. So the camera is attached to Raspberry Pi, yeah, and there is some video storage, and there is this module that is running, yeah, dynamic frame alteration. So what it does, basically it computes two things, yeah. one is something called structural similarity index metric. Yeah, so it's basically how much is similarity of the incoming video with the stored one. So like frame by frame. Yeah, and it also checks the frame difference. So like what is now, what was the previous moment. Based on those two, basically he decide the moment when he can replace the incoming feed with this one, and then it's not easy to detect, yeah, because they are quite similar. Okay, this is like something is getting executed, but after some time the stored video is blended and it's done seamlessly, like I said, using these two metrics, and then it stays undetected. Okay, so this one has like a real life demo, but I can't show it here. Yeah, but this is like one way to attack this video manipulation. Okay, and this is the result about detection accuracy. Yeah, so this is like detection accuracy of different approaches. So like so these are basically LOF, SVM, KNN, and this is average. Yeah, so these are the detection approaches. Yeah, I think this one is called least of frame something. This is support vector machine. This is K nearest never. And then you have these attack types. Yeah, replay, frame injection, video stream hijack, and DFA. So we apply that and apply this detection approach and check like what is the detection accuracy. So like out of 100 times, how many times this can detect. So you can see here, like for existing ones, the detection accuracy is very high, whereas in DFA accuracy is very low. That means lots of time this approach cannot really detect this dynamic frame alteration approach. Yeah, similarly support vector machine, almost similar results. Yeah, and again similarly with K nearest never. Okay, yeah, so this is one way to attack. Again, this is kind of trying to mimic the real feed, yeah, of coming very close to the real one but replacing it with something else. Now imagine what can happen if you do that. Yeah, if there is a flood monitoring at the server or at the base station, it will say there is no flood, so it can lead to more problem. Yeah, and if it's a bank, you know, like, yeah, you can rob the bank. Okay, so this one is again the same result in table format. I think we don't need to look again. Yeah, that was plotted previously. If you want to look more details, this is in this paper. Yeah, again this one and the previous one, continuous authentication. No, that was published somewhere else. So this is again like some cyber security conference. I think just happened last month or something. So this is published there. I think this paper is also available online. Okay. So again, we are not going into lots of details. Yeah, there are a lot of libraries like Python and what kind of video feeds we stored and what exactly is monitored. All the details are in the paper. Okay. Any questions? No? Okay. Now next one, I thought to cover attack on AI models. So nowadays you cannot live without AI models, right? But attackers are finding a way to attack these as well. Okay. So let's see how these things can be attacked, the AI models, and then how we can stop that. Yeah, how we can detect and prevent. So the one we are going to look is called something like prompt injection attacks on large language models. Okay, so large language models we all use, yeah, like OpenAI or Gemini. So any chatbot is using large language model, yeah. But lots of them can be attacked with doing something like prompt injection. Okay, so what exactly it is? Do you have any idea what is prompt injection attack? If you don't know, I'm going to cover, but just wanted to check if you have heard about it. I will throw that slide in case you want to answer something. You can search on internet very quickly, again on large language model also. On ChatGPT you can search what is prompt injection attack. I think nowadays if you look at the models, they have become more robust over the time, but when they were released there were huge instances of prompt injection attack. And if there is any model new that is coming in the market, it's very prone to prompt injection attack. Any idea what do you think it is? Good, that's a perfect definition, yeah? That's perfect. So writing a prompt which can break any existing rule of the large language model. So for example, these large language models, they should not be giving answer for everything, right? If you say like, how do I murder this person? Then it should not give the answer, yeah? Or you search like, how do I make a bomb? Then it should not give the answer, yeah? So there is a rule, it should not give answer for everything. So now, how you can write a prompt in a way, it still gives you the answer, yeah? So they are not still very intelligent, so it's like, you want to find out something, put some words before it, put some words after it, or ask the same query in a different way. Don't write bomb word, yeah, that is alarm to that. Write something else, yeah, maybe explosives or something else, or some other term that is not alarming, yeah, then it can give you the answer, yeah. So that is basically prompt injection attack. So you kind of curate your prompt in a way these large language models can give you the answer, okay. Good. That's another nice definition, tricking an LLM using a prompt, not directly, okay. Yeah, that's the same thing. So try to do some attacks onto these large language models. I think you cannot do the ones that are now very popular, ChatGPT or Copilot, because these have been trained from a long time. But some that are released like recently, not well trained, or these rules are not well defined, you can still use it, yeah, okay. So there are still some large language models, okay. Let's see, it goes next slide. Oops. So like we already have seen, yeah, these are techniques to manipulate large language models by inserting adversarial prompts. So you curate your prompt in a way, so you manipulate the large language models, yeah. What exactly will happen? They may leak confidential information, or they can ignore instructions, or they can execute malicious behavior, yeah. So something that the large language model is not supposed to do, if you kind of manipulate large language models in the form of like writing the prompt in a different way, it can give you the answer, yeah. So that is basically prompt injection attack. So if it's happening, we need to detect it, right? So let's look what are the limitations of previous detection systems, yeah, that are basically detecting prompt injection attack. So previous systems are relying heavily on linear or surface analysis of prompts. So it's like in your prompt there are a lot of words, right? They do some sort of linear analysis, yeah, like one after another each word, yeah, or like I said, there is a one word like bomb or murder, something like that. They rely based on that, yeah, and if they do that, they often miss kind of non-context dependent attacks, okay. So they cannot work well, Okay. So what we typically want to achieve, yeah? So we want to achieve high accuracy detection of adversarial prompts in large language model workflows, yeah? So we want some detection approach that should be very, very accurate, yeah? And you have to be careful to develop that because sometimes if you are overprotective, right? Anything you ask the prompt or large language model, it may say, sorry, I cannot give you the answer, sorry, I cannot give you the answer. That's one way, yeah? But you have to be giving the answer when you are supposed to do, okay? So the accuracy is very important, yeah? So you should not have like false positive, yeah? Don't say like it is an attack whereas it is not, because if you say that, you are not going to give the answer, okay? So again a question, so how adversarial prompts can be detected in large language model workflows? Any ideas, thinking? So what exactly it is, yeah? You're typing something in the chat GPT, yeah? So but that is not a simple word, yeah? You are kind of twisting it in a way it should give the answer whereas it's not giving, okay? So I mean there is like, even if the words are twisted, how can you make sure it doesn't give the answer, yeah? So how that can be detected, like even the twisted words have some kind of malicious intention. Okay, let me throw that slide. Okay, any idea? Okay, sentiment analysis of input prompts. That means you exactly work in this field. That's nice. So actually the thing is, yeah, so you kind of take the all words, yeah, don't literally go with the linear analysis, yeah. You find out what is the sentiment of all of it, yeah, whether it want the answer that's going to come, whether it's going to do some harm, yeah, to someone after that person knows the answers, yeah. Using LSTMs, not sure how it can be detected, yeah. Natural language processing, I would say natural language processing is part, this is large language model, right? Training the LLM regularly, I think this one is nice. So you know, like sometimes they are giving some answers. If you train, basically it's just going to give you better answer, yeah. But maybe you can also train in a way it should not give the answer if it's the prompt is in just kind of modified way, okay. What is this RLHF during training? I don't know what is this RLHF. Maybe some kind of rule defining during training, yeah. Okay. But I think you have some ideas, yeah. So sentiment analysis is kind of more powerful, yeah. You kind of have the sentiment of the word that is typed, and then based on that you can decide, okay. So again, one of my master's student developed some approach. He also used this sentiment analysis, okay. So let's see that approach we can briefly cover, yeah. Don't know how much time we have. We have some time, yeah. Takes a long time to go. Oops. Okay. So the proposed approach is called novel GNN based detection framework. Yeah. So how exactly it works? So we take a data set. Yeah. So data set is of prompts. Yeah. They're like, and there are some kind of, you can say, malicious prompts and some non-malicious prompts. So everything is there. I think this data set has like 5,000 prompts that we have taken. So then we do some pre-processing of the data set. So first we do the duplicate removal. For example, if in your questions there are lots of same words or same basically meaning words, you can try to remove that. Yeah. And then you can do text normalization. So this is something is done already. So if there are some kind of uppercase letters, you make everything lowercase. Okay. And then you do some tokenization. So tokenization is something like out of all the words in the prompt, it's going to make tokens. Yeah, it's like first word is one token, or if there's a maybe long word, then it can make two tokens. Yeah, so the first subword is one token, second subword is another token. So you do that tokenization. Yeah, and after that is done, you do some graph construction. Yeah, so it's like each token is a node in the graph, and then here there are a few steps that are done. So these are not novel. Yeah, this is like but embedding extraction and edge construction. These are already well popular. Yeah, there are libraries to do that. So from that tokens, like you can say all the nodes, from this graph construction, we capture semantic and contextual relationship between the tokens. Yeah, I think someone said like sentiment analysis. Yeah, so this is very close to that. Yeah, so these kind of relationships are captured. Yeah, so this BERT embedding that is already available provides a rich contextual representation that captures the meaning of words based on their surrounding context. Yeah, and here sentiment features are also incorporated into the node representation. Okay, and finally edges between the nodes or tokens are established, ensuring that local contextual dependencies are preserved. So again, we are not going in detail, but for each step there is a process. Yeah, but in summary, it's like whole prompt is made into tokens, and a graph is made out of it, and within each node we capture contextual relationships. Yeah, and then that graph is fed to a GNN model. Again, in our GNN model, it's well defined in the paper. So that GNN model is trained. Yeah, like I said, we have around 5,000 prompts. Out of 5,000, we have taken like 80-20, 80 for training. So for all 80% of those 5,000 prompts, we do the same step, and then one GNN model is trained for that. Yeah, and then that GNN model is basically going to tell, based on these features that are captured, whether it is basically kind of malicious prompt or it is not a malicious prompt. Okay, I think maybe we can stop here. There are just one or few more slides I will cover tomorrow. Okay, yeah, all right. Okay, so we stop here. Oops. So this should be break time, right? 3 to 3:30. I don't know if there is tea, coffee, or something. There is. Okay, you can have the tea or some snacks. Yeah. So tomorrow, like I said, we will mainly cover sustainability part. Yeah. The remaining part I will cover briefly, and then we move on to the sustainability. Okay. It's hanged. It's not moving. Nothing is moving. Okay. Okay, I will close it anyway. I can't close also. Oh, okay. Okay, I will take this out.
Shall I start?
We wait for the book. Let's connect the laptop.
Okay, okay, okay. You were not there yesterday, right? Your name? Pritudeep. Triple E.
No, CICPS.
CICPS.
I registered, but yesterday with our classes.
Okay.
Even today morning's one was clashing.
Okay, okay. Let me check if enough battery is there or not. Yeah, I think we can start. Yeah? No need. That's okay. We can start. Battery is there. We'll start. Okay, so good afternoon everybody. I hope that you remember what was done in the last class. So can we have a quick recap of the last class? What did we do in the last class? Yes, you can speak up if you want. So we saw what is cyber security, network security principles, and some attacks, some types of attacks. And where did we end our slides with? Yeah, so we just wanted to know that, you know, how to, so some security principles we had. The last module was security principles, okay? CIA, AAA and IKE, PKIs. Now, today we are going to start with security at different layers of the TCP/IP layer, okay? Now, so this is how it looks like, the protocol stack, okay? So anybody who is unaware of this protocol stack? Everybody is aware of this protocol stack? Yes? Okay, so what is the task of application layer? Nothing? Yes. Okay, so to provide services related to applications, okay? And then the next one, transport layer. Sorry? Process to process communication, right? So that's about transport layer, and then network layer has already come up. So network layer is basically, you know, helps you to communicate between two hosts in the network, any two hosts in the network. And the last one is, the link, I think the K went down, okay, that's the link layer. Okay, so link layer is responsible for what is the task of link layer applications, sorry, link layer protocols? Data transfer between neighboring network elements. So it's not about one host to another host. It is like you need to find out that, you know, scheduling, yeah, how, which route will you use. Okay, so it is like this. So suppose there is a common channel, so now who will schedule at what time? Okay, scheduling decisions, these are being taken at the link layer protocols. Then finally comes the physical layer. Okay, now why are we looking at this? Okay, all right, so physical layer is basically bits, of stream of bits moving on in the medium that you are sending the data. Okay, so application layer protocols are there, transport layer, network layer, link layer, and finally physical layer. Okay, so where should we provide the security? That is the question. Okay, so I told in the last class that, you know, now the researchers are actually catching up to what already the standards and protocols have been made. Okay, people are catching up to it. All right, so if I have to make a very good security protocol, okay, where should I put that security protocol in my stack? Okay, that is the question. So can anybody suggest anything? Should I make, yeah?
Application is like firewalls and all application.
Just at the application layer.
And of course, at all the levels we can provide encoding these things and all.
Okay, so you are saying all the layers, right? If I have to summarize what you are saying, why?
Because mainly we do at 3 layers, because if we are passing through routers and all, it contains only 3 layers.
So, sorry, bottom up 3 layers or top down 3 layers? Which one do you want? Bottom up. So only file link and network. Only up to network layer. You want security and no security needed in transport and application layer. Okay, so that's one suggestion from your side. Anybody else?
Each layer,
Why?
attacker can go to any layer if you want, because all the layers will be network, whether it is a physical layer, transport layer. Also, if you are transfer package, it will from starting from physical layer, it starts logging frames, sessions, and hypertext headers. It can be easily.
Okay, that's also one answer. But then that's a lot of task, right? Okay, so that is also something. So if we can provide a blanket security, that will be great, right? But we have to see whether we can actually do something like that or not. Okay, so yeah, so which one is good? A blanket security, that means you provide your security protocols in a particular layer so that it gives you a blanket security like he just told. Okay, and whether I should provide it in all layers. Okay, so now if I am providing a blanket security, the problem will be that I am not getting any user level security in the upper layers, right? And if I am providing in all layers, the good thing that I am getting is that, you know, if you want to add new internet services, it will be easier to provide the security even at the higher layers. Okay, so some pros and cons we have got to know by now. In this class today, we will get to know that some of the common security protocols that are used in transport layer, network layer, okay, and some operational security protocols, okay, and also, sorry, one application layer protocol also we will see. Okay, so now let's start with the first application that we have, that is email. Okay, I think I have double clicked. Yeah, so email is the application. First application is email as an application. Okay, now if you remember yesterday's class, we had an example of Alice and Bob. Okay, they want to talk to each other. So here Alice and Bob, they are communicating using email. Okay, now how can I provide the three objectives that we had studied yesterday, that is CIA, confidentiality, integrity and accessibility. Okay, so confidentiality. Okay, so first thing, if I want to send a confidential email, okay, so what can I do? So here if you can see, Alice, the message is denoted by M. Okay, so what does Alice do? Alice generates a random symmetric session key, okay, called as KS, okay, and uses that to encrypt the message. Okay, so that's KS of M that is created. All right. Now next is that Bob has already advertised its public key. Okay, so Alice knows about Bob's public key. Now using Bob's public key, Alice encrypts KS, the session key that was generated. Okay, now what Alice does? She sends them both over the internet to Bob. All right, so this is from Alice's side. Now next is at Bob's side, how will Bob get the message? Okay, so what Bob does? Bob will use his private key to decrypt the KS part, the session key, and then he will use that session key to get the actual message that was sent by Alice. Okay, now this is how confidentiality of the email can be maintained, confidentiality of the email message that was sent by Alice. But only confidentiality is not going to suffice, so we need to have integrity and access, right? Okay, so how to do that? Okay, so now here we are going to put message integrity and authentication. How to do that? So what Alice will do is, Alice will digitally sign a hash of her message. Okay, so you can see this key sign that you are there, that you can see here. Yeah? That key is her private, Alice's private key. Okay, so it will digitally sign a hash of her message with her private key. Okay, that will provide the integrity and authentication. Okay, and then the actual message also she will send. Okay, so she is sending the hash of her message with by encrypting with her private key. Then the message that she is actually sending, both of them she is sending over the medium. This is thinking that there is no breach of confidentiality. Okay, so she is sending and then it is reaching Bob's site. Okay, at Bob's end, what Bob will do? Bob has Alice's public key. Okay, that is denoted by KA plus. Okay, so he has her public key and then he gets the hashed message from there. He decrypts using that, and the message was already sent by Alice, so that message also he creates a hash and then compares both of them. If both of them are same, then great. Okay, so this is how integrity and authentication is maintained. Okay, now I have to ensure all of these together when I am sending an email. So what do I have to do? I have to combine all of these things together. Okay, so what do I exactly do when it comes to confidentiality, message integrity and authentication? Okay, so first is for message integrity and authentication, I will be using the hashing method. I will hash the message and then encrypt it using Alice's private key and send the actual message also together. Now this entire message together, okay, what am I doing? Okay, I have the session key generated by Alice, so that session key is used to encrypt this entire message. Okay, then Bob's public key is there. With Bob's public key, I am encrypting the KS, that is the session key, and then combined together I am sending it to Bob's side. Okay, now you tell me what will happen at Bob's side. Both we have studied, right? We just got to know that if, so Bob has what will Bob do?
Bob will first decode it, decrypt private key,
Yes.
and then it will like compare. He will get a message that is and hash also. So he will like compare both of them.
Yeah. So first he has to get this session key, right? So first he will try to get the session key, okay, with his own private key. So he gets the session key with his private key, and with that session key he gets this combined message, okay. Then he creates the hash and then compares to find out what was exactly there in the email message, okay. So this is all the steps that goes on when you are sending an email message, okay. Any questions here? No questions? All right. Okay, I'll go to the next slide. Okay, so anybody has heard of this protocol, TLS? Yes, tell me, what is TLS?
So mostly it is used for our email.
Okay. That's it. Okay, first, anybody else?
HTTPS uses this.
HTTPS uses it. Very good. And anything else? The name says something.
It's at the transport layer.
It provides transport layer security, but actually TLS is not in the transport layer. Okay, it's in the application layer. Okay. All right. So we will now look at TLS. Okay. So it is a widely used security protocol, okay, for transport layer protocol. Now, as you rightly said, used in HTTPS, what it provides? It has to provide the three objectives. Okay, so how does it provide confidentiality? Via symmetric key encryption. How does it provide integrity? Via cryptographic hashing. And how does it provide authentication? Is via public key cryptography. Okay. So in this class, because it is a very small session, okay, I want to go through the overview of it. Okay, I don't want to get too much into encryption because I want to show the network layer part, the network security part more. So I will just get into this part first. What exactly happens in TLS? Okay. So first is handshake. Okay, so what happens in handshake? Alice and Bob, they will use their certificates and private keys, etc., and they will exchange. Okay, okay, any shared secret material that needs to be exchanged, that is done during handshaking. Okay, then what will happen? Key derivation will happen. Okay, so what will they do? They will derive a set of keys, okay, using the shared secret that they have just shared using handshake. After that only data transfer can happen. It can be as a stream data transfer. Okay, instead of just one time transaction, it can be a stream of data transfer that can happen. And most importantly, after everything is done, you have to close the connection. Okay, so the last step is connection closure. Okay, so how do we do that? Once everything is done from the client side, there will be a connection closure message that will go. Okay. All right. So this is how TLS provides an API that any application can use. Okay. So see, if you want to put HTTP with TLS, okay. So HTTP2 over TCP looks like this, no TLS. Next one, you have TLS with it. So as you were telling, as I was telling you that it is a transport layer protocol, but it actually does not reside there. So you have HTTP2, then TLS, and then TCP/IP. And anybody knows about QUIC? Have you heard of QUIC? You can Google if you want to. I'll give you time. Sorry? UDP security. Just that. You are there, but you might just Google it a little bit.
reduces latency.
What is it? That is a property of it, but what is it exactly?
Um, Similar to HTTPS, but it is used over UDP for transport layers.
Yes, it is used for over UDP for transport layer security. Okay. So yeah, any other thing that you want?
Google says that it reduces round trips required to establish a connection, so it reduces.
So that's reduces latency, you have
Yes,
already
latency,
told.
right.
Yeah. Okay. Anything else? Anybody else? So it is a homework question for all of you. Okay. So for a video streaming application, my question is you can just go back and see that whether I should use a simple TCP and TLS combination, or I can use quick. Okay, just see that which one should be better in that case. Think about it, okay, and then tomorrow we can answer this question. Okay. All right, let's move forward. So how does a TLS handshake look like? So first thing is that, as I told, that in the handshake phase they will send and receive the information regarding different certificates, okay, the agreements, etc. Okay, so DH is here Diffie-Hellman. Okay, so that's a key agreement protocol. So what the client side does is, whatever cipher suits, protocols, algorithms it supports, okay, it will tell the server that these are the choices. Okay, what server is going to do? It is going to choose from that. Okay, so that's the next step. Okay, selected cipher suite, then DH key agreement protocol parameters and all. Okay, so server will say that okay, these are what my agreements I can do. Once that is done, then the client will check the server certificate, generate the key, and then now after that you can communicate. Okay, so this is how a TLS handshake will work. Okay, so basically if you see, what I am going to do is that I will just give a very brief and quick overview of different protocols which are used in the different layers. Okay, and we will do up to network layer. Okay, all right. Now let's get to this part, that is network layer security. Okay, now has anybody heard of IPsec? No one?
I've heard of it, but I don't really know what it means.
Where have you heard of it from?
During class.
Okay, all right. Okay, so it is already given that it secures IP datagrams between any two network layer entities. Okay, so now my question is that if I am securing datagrams, okay, so what I can do is datagram is secured. Okay, I don't need any other much of security, because lower layers some security anyways is provided. Okay, but up to network layer, if I am providing that, okay, this kind of a blanket security, will it be very good, or I should still go with providing security of all layers? I am providing security over the datagrams itself. Okay, I am securing the IP datagram. So do I need any further on each and every layer?
It would be better if they have security in all the layers.
Hmm.
But using
Even physical layer, I mean, if somebody just opens your connection.
Well, that is something different. That is, you are doing it purposely. Yeah. But yeah, what you were saying, please continue.
But like if we use and if we encrypt the datagram, then it would be fine for the communication events.
So it provides a blanket security over it, right? Acha. Okay. Anybody else has any other answer? No other answers? Okay, so we will move forward in that case. So yes, IPsec is a network layer security protocol and it provides security over the entire datagrams that you are transferring between two entities, any two entities on the network with which you are communicating, okay, and it also provides the CIA, okay. So we will see how it provides the CIA. Now here if you see, it is written that it works in two modes. One is transport mode and another is the tunnel mode, okay. So I am assuming that most of you are from computer science background a little bit, okay. So has anybody heard of the word tunneling before? So you are nodding, you are saying tunneling. So what does tunneling do?
You connect to an external network by, I mean, I'm not sure of the exact definition, but it helps you connect from an internal network to an external network through some host.
Okay.
You can share resources that are there in an internal network with some external host.
Yeah, I understood. Okay, anybody else?
Tunneling, basically they hide the IP address and then they provide a wrapper around it, and then we are able to access the external networks.
Yes. Where have you, where is the exact usage of it? Where have you seen it? VPN, definitely. And anything else?
SSH?
Okay, to some extent, okay. Has anybody heard of IP address translations? So if you have IPv4 and IPv6 being used in your entire network, okay, how do you ensure that you don't know which one is using IPv4, which one is using IPv6? So are you just not going to communicate? So at that time you create tunnels and then you transmit your data, okay. So you can just go back and check in that case for IP address translation. Okay. Now let's get to the transport and tunnel modes. Okay, so what happens in the transport mode? In the transport mode, only the datagram payload, okay, that is encrypted, okay. Whereas what happens in case of my tunnel mode? Okay, in that case entire datagram is encrypted and authenticated. Okay, so these are the two differences in transport and tunnel mode. We will be focusing on the tunnel mode because here we assume that the entire datagram is being encrypted. Okay, so what happens to this encrypted datagram? This encrypted datagram will be encapsulated in another datagram with a new IP header and then it will be tunneled to the destination. Okay, so let's see. So you can see here that there is a payload with all the header paths. So now you are encrypting it and then sending it over a tunnel to the endpoint. All right. Okay. So yes, everybody came up with this example. So this is VPN. Okay, one of the use cases of such a protocol. Okay. So VPNs, anybody wants any information about that? Most of you know about it. Okay, so what VPNs do? Everybody uses it, right? Okay, so what do we get by using a VPN?
First of all, we can hide our IP address, and secondly, we can access the network which is restricted to us.
Okay.
Which is not allowed in our IP address. Can access to.
Okay. Okay. So that is that. Just give us something simple humans like us will use. Yeah. Something simple.
Can access from different locations.
Yes, please. Okay. So anybody has worked in IT industry or something? Yes, so work from home, how does that happen? With the help of this, right? So what do? So whatever communication you are trying to do with another entity over the internet, because internet is not private at all. Okay, so you are trying to create a virtually private network over the internet between the two entities. That's what VPN is. Okay, all right. Oh, the example was given only. Yeah, see, all right. Okay, so let's see. There are two particular protocols associated with IPsec. One is authentication header protocol and another is encapsulation security protocol. Okay, so we are going to look at ESP only. Okay, so AH is basically, it provides source authentication and data integrity, but it does not focus that much into confidentiality, whereas ESP is more focused into all three of them. Okay, so we will look at ESP only. Okay. So one more term that we need to know is security associations. It is nothing but a logical connection between any two entities, okay, over the network layer. Okay. So before sending any data, you need to actually create an essay. Okay, so an essay needs to be established between the sending and the receiving entity. Okay. So what is required? So the receiving entitles will maintain the state information about the essays. Okay, so what will be in that state information? So TCP endpoints will be required to maintain the state information. Now what's happening here? IP is connectionless, that's what we know, right? But when we are maintaining state information, then it is no more connectionless, it becomes connection oriented. So that is why IPsec becomes connection oriented in nature. Okay, all right, let's see how it does this kind of encryption. So first let us see this green part here. Okay, so we have the original IP header and the original IP datagram payload. Okay, with that I am adding an ESP trailer, okay, that has padding, pad length, next header. Okay, now this I am adding and then putting over it an encryption. So that's a fully encrypted part that you have. Okay, in this part I am putting an ESP header. What does it contain? It contains two things, an SPI, which is nothing but it just identifies the essay. Okay, the essay which your datagram belongs to. Okay, and then the sequence number. Okay, so there should be a sequence number also associated in order to avoid any kind of replay attacks. Okay, so these are the two things that are associated with the ESP. Now once this is created, then an authentication will be done. Okay, how is it done? By encrypting it using a shared secret key. Okay, so this is done. So ESP header and ESP authentication field, that is there in the last in yellow. So these two are added, authentication is done overall, and then you add a new IP header which will contain the address of the tunnel endpoint. Okay, the tunnel endpoint, so that it reaches to the required destination. So this is all the task that is done in the IPsec datagram. Yes?
What does that next header do as part of the ESP trailer? The last, the next header that you...
Next header that you will be reading, right? Yeah. Okay. All right. So yes, there's some sound that is coming, no?
The gain is so high.
Okay. I don't know whether there is a volume. I don't see here. Anyways, I think this is okay, right? It's okay. All right. So let's see how does it work. Okay. So there are two routers here, R1 and R2. Okay. So what does R1 do? R1 will append the ESP trailer to the original datagram as it was shown. Okay, then it will encrypt the resultant using the corresponding algorithm and the key that is specified by the essay that was created. Okay, so you are actually creating a logical connection before you are setting up the connection between these two entities. Okay, Now what you do, append the ESP header to the front of this encrypted quantity, create the authentication MAC as I was telling you, using the ESP, that yellow part that you have, ESP authorization. Then append the MAC forming the payload, okay, and then create the new datagram, okay, with the destination of the endpoint, okay, tunnel endpoint. So this is when R1 wants to send something to R2, okay. Any questions up to here? All right. So let's see how a VPN may look like, okay. So why do I need a VPN? Because I want to access some particular server, okay, and I want to create a private channel over it, okay. So here, as you can see, so if there is a particular company where you are working, it is not that there is just one entity and you are just communicating with it, okay. There could be headquarters, there could be other offices in other cities, okay, any part of the world, and you can create a private network over it. Now if there are less number of them, then what will be there? For everything you have to create an SA anyways, okay. So let's see, if there are less number of such different entities, okay, the maintenance is less number of SAs you are going to maintain. But if there are a large number of them, then it becomes difficult. You have to have a database for that, okay. So two different types of databases that we have here: security policy database and security association database, okay. What does the security policy database tell? It will basically tell you that, for this particular association what to do, okay. So that means what are the corresponding policies that should be used or that should be there for this particular SA, okay. And whereas what is for the security association database, it is like how to work with this, okay. So that is all the different steps that you are taking for continuing with this SA and the communication between the two entities, okay. So as you can see that when you are sending a datagram over this from one endpoint to another endpoint, the SAD or the security association database, that will basically tell you how to process the datagram, okay. So these are the information that will be there in these two databases, okay. Now let's see, if you have a lesser number of such databases, okay, then it is easy to maintain, manually, you can have manual establishment of IPsec SAs in the endpoints, okay, because you have to have, information about all the SAs that are being created, all right. Now if there are too many of them, then this manual establishment of IPsec becomes an issue, right. So what do we do, okay? For that we should use IKE or Internet Key Exchange. So in particular we can use IPsec IKE, which is mentioned in RFC 5996. If you want some more information regarding this, you can just probably go and visit this RFC, okay, just take a look at it. So what does this IKE do, okay? Anyways, in the SAD, what we were doing, we were exchanging the informations and we were trying to know that how to maintain this communication, okay. So the same thing is going to happen with the help of this IKE, okay. What is it going to do? It will exchange certificates, it will negotiate the authentication algorithms and any encryption algorithm if it is being used, and in the end it will exchange the key materials, etc., okay, for this communication, for creating the session keys and in this particular SA, okay. So this is what your IKE is going to do, okay. So essentially what is happening in an IPsec, you are creating SAs, okay, and if you have a large number of connections that you have to maintain, you can use IKEs to maintain these, okay, and your database will always be there to give you the information about the different protocols that are required to be used for this. Okay, so this is our IPsec. Okay, now we have completed application security, transport layer security, and network layer. Very briefly, network layer security. So next part is operational security. So can anybody tell me what is operational security?
So movement protocols, whatever steps the users take from their part. The operations basically, we try to secure those.
Okay. And anybody else? I have to secure my organization from certain threats. Okay. So how do I do that? Okay, these layer by layer I can have security protocols, but on the outside also I need to do something, right, away from all these layer by layer security. Okay, so that will fall under my operational security. Okay, any example of such kind of protocols?
Not writing down passwords.
Okay, that will come under, if you have seen yesterday's class, that is, educating the user. Okay, so that will be probably under that. Anything else? Authentication and authorizations. Anything else? Very widely used. OTPs. Okay, just I want to give you an example. Think from the point of view of an organization, okay, because I want to head to that topic. Okay, so think from the point of view of an organization and you want some first level security for your organization. What car?
Cards.
Okay, okay,
Access levels.
access, access control and first level security for organizations.
Use tools like
Firewall, yes. And anything else?
Using packet filter.
Yes, it comes under that. Very good. Anything else? That comes under authentication, no? Yeah, that will come under authentication. Okay. Okay, so so let's start with firewalls then. Okay. So operational security, as you can see here, it is used to protect sensitive information of any entity that it may be an organization, maybe a particular person, for managing how data is processed and how daily operations are handled. Okay, so let's start with the first one, that is firewall. Okay, so what's a firewall? It is given in the slides, but if you have anything to add on to it. Nothing? What does firewall do? Filtering and so basically it acts as a barrier kind of a thing. You are so if you have seen movies, old movies, with kingdoms and all that. So there was a huge wall, right, before you could enter into the kingdom with a huge gate. That's what firewall is. Okay. So what it does, it basically filters out the bad packets. Okay. Now it's up to the programmer or whoever is creating this firewall to tell it that which are bad ones. Okay. So yeah. So what do? You have to get the good guys in and remove the bad guys out, or just stop the bad guys out. Okay. Okay. So why do we use firewalls? Okay. One is I want to secure my system. Okay. How can I secure from different attacks? So if there is somebody who is doing a DOS attack, Okay. So what can I do? I can just simply stop further packets from incoming. Okay. Then I can also prevent any kind of illegal modification of any kind of sensitive data. What else can I do? Any unauthorized access inside the network, that can also be prevented. Okay. Now there are 3 goals of firewall. Okay. First one, if you see here, okay, so any traffic that would come into your system has to pass through the firewall. First rule. Okay. Second rule, okay, only authorized traffic will enter. Okay. Now how will you define authorized traffic? Okay, that will be, whatever security policy you are using, accordingly you will define what is authorized and what is unauthorized. Okay. And what's the third and most important thing? Your firewall should not be compromised. If that is compromised, then gone. Right. So these are the 3 most important goals for firewall. Okay. All right. Now let's get to this. So there are many evolutions of firewalls that go on. 3 basic ones are stateless, stateful and application gateway. Okay. And the last one I have added is a next generation firewall. Okay. Now what happens in a stateless firewall? Simply you check the packet source destination. It is given to you that if it comes from this particular source or if it wants to access this particular destination, you just block it or drop it. Okay. Stateful, okay, you track the entire connection, entire TCP connection if it is using TCP. Okay. And then see that whether there is something wrong there or not according to whatever security policy is being used, and then you block them accordingly. Okay. So you see all the fields. Now next comes the application gateway. Okay. Application gateway actually also looks into the application data. Okay. So apart from the different fields, header fields that you have, okay, you also look into the application data when it comes to application gateway, and then see that whether there is something wrong there or not. Okay. If you find something wrong in that case, you just block it. Okay. The last one is next generation firewall. Here you can add more features, intrusion prevention, application filtering, and some more level of deep inspection can also be added. Okay. So these are my different types of firewalls. Okay. Can anybody tell me if there are any limitations of firewalls, or using a firewall gives you all types of security? The word blanket security I would say here. Any limitations?
False positives.
False positives. Can you give an example?
I want to access something that should be allowed, or something wants to access my network that is benign, but it is being blocked.
No, that is what you are defining false positive here. I am just asking that if you have an example in mind.
Specifically, example as of
Like
now,
sometimes we install antivirus, it says you have to disable that firewall first, then you should install the antivirus.
Okay.
Or
Updates. Okay. So suppose I do that, I disable the firewall for some time and then do it. So then different kinds of attacks might happen at that time. Okay. Anything else? Any other limitation? Okay, we'll see what are the limitations. Okay. So one of the problems is IP spoofing may be there. Okay. See, I may not be able to know that the source that it is claiming, okay, whether it is actually from that source or not, I may not be able to know, because I cannot check up to that when I am using a firewall. Okay. So that can be there. Okay. If you are using application gateway, okay, in that case what will happen? For different applications that are there, special treatment has to be given for each one of them, because you are looking at the application data also in case of application gateway. Okay. Now, what is the trade-off if you have to make a good firewall? What is the trade-off? The trade-off would be that the level of security that you want to provide from the outside world. Okay. Now, because as I was telling that giving a good firewall does not always mean that you will be fully secured. Okay. So that is why there are evolutions of firewalls that are there, and if you want, you can please take a look at it. Yesterday's class, I think I had forgot to mention the references. Okay, so most of the references is from Kuros and Ross book. Okay, I will also give this reference in the end. All right. So the next part is intrusion detection systems. What is intrusion detection system? I wouldn't ask. I would like to ask what is the difference you feel between firewall and intrusion detection systems. So you can always define from the name itself what is intrusion detection system, but can anybody tell me what is the difference between the two?
Firewall is like the door of the house. It allows some like legit packets only to enter. Intrusion detection system is like a robbery alarming system.
Okay. How exactly you will say that the robbery alarm system will work in your case, because somebody is trying to enter and
they can break the door, like get past to the firewall, but there is alarm that is like used as intrusion detection system.
So firewall is trying to stop, it is trying to prevent, and this, it has, the intrusion might have already happened, so it is detecting after the fact. Or during
not always, actually, not really. Okay. Okay, anything else? Okay, so let's see, think about it. Okay, so intrusion detection system actually looks deep into the packet. Okay, looking at the packet contents. Okay, so you might ask me the question that application gateway also looks at application data. So then what is the difference between intrusion detection system and an application gateway? That's also kind of firewall, right? So yeah, now the question again comes that then what is the difference between IDS and firewall? Okay, anybody knows how does an IDS work? So in firewall, what do? We just mention that if these are the characteristics that are there, so in that case you block the packets. Okay, we will see how IDS works now, and then you will be able to know what is the difference between firewall and an IDS. Okay, all right. So let's see how does an IDS work. Okay, so first let's so IDS also has another brother or sister of it, that is IPS, which is intrusion prevention system. Okay, now IDS will simply detect the suspicious activity and IPS will detect and block the suspicious activity. Okay, but both of them are more concentrated into how to detect that attack. Okay, so that is why sometimes it is used as a slash. Okay, that means interchangeably you are using it. Okay, mostly the focus is on how to detect if there is an intrusion. Okay, so how does an intrusion detection system work? I have not put it in the slide because I just wanted you to tell verbally. Okay, so there are two ways of intrusion detection. Okay, the first one I have written it here. Okay, because first one is signature based and the second one is anomaly based. Okay, so what happens in signature based? You know that there are certain types of security attacks that can happen. Okay, and you know what are the properties of them. Okay, so what do? You give a signature of these. Okay, and now what will happen if there is a stream of packets that is coming? it will be compared with all of these signatures to see that whether there is any similarity with any one of them or not. If at all you find something, you flag it, okay, you send a signal that there might be a problem, okay. That is signature based, okay. Now what is anomaly based? In anomaly based, what you do is you look at the traffic, okay. You look at the traffic and then you find that, you know, if there are any kind of anomalies or not, and then you have again, you know, a list of these anomalies. When there is a stream of packets, you compare, you find anything problematic, you send a signal, okay. So that's how, so these are the two categories, okay. So question is that if I have a firewall, or if I have a simply, you know, the gateway router that I have for my organization, and I put an IDS, okay. So that will simply, you know, help me in just, you know, filtering out all the issues, you know, packets with different issues, right. It can help me, but why, if you see here in this diagram, there are different IDSs at different places in the network, okay. So why should I have multiple IDs rather than just, you know, one single IDS I can have, no? Less cost.
Redundancy, localization of the issue also.
Redundancy will again increase my cost, no, in this case. So why should I have it?
So you can localize exactly where that issue is. Which part
You
of
are
it?
anyways comparing it with different anomalies, right? So in that case, the packet is destined to some place in your organization, so you know where it is destined to, okay. So any other idea?
फिजिकल क्योंकि फर्स्ट जो हमारी स्लाइड देखते हैं उसमें फर्स्ट इज इन फ्रॉम द नेटवर्क, अनदर इज वन इज फ्रॉम द सिस्टम, एंड इफ समवन इज somehow attacks from the outside the network and send the different packets to the network, so it can be able to detect from that.
Okay, I'll just give a hint, okay. Just remember the different procedures in which you know, you detect the anomalies. Signature based and anomaly based, these are the two techniques, right? So can you think of something from that perspective?
Anomaly might occur in one part of the network but not in the other.
No, not exactly.
Maybe ideas separate for IPs for different and DOS and different IPs.
Okay, all right, but then where are you going with this answer? I just need to understand.
We will require separate ideas for maybe DOS attack.
Okay, so you are saying that, okay, so you are near there, okay, then
Separate for this attack specific type of
okay, so you are sending, so I am giving another hint. So you are sending a stream of packets, okay, your IDS is right below, behind the firewall, okay, just one IDS, okay. So you are getting a stream of packets from the internet. Now any kind of attack could be there, you don't know what kind of attack could be there. So then what will happen? Think next step, what is going to happen? So packets will come. So what happens in just think about signature based IDS, okay. What happens in that? Every packet will come and I will compare with all the signatures, okay. So if it is just one, that means all the packets, the, you know, entire load that is coming, everything has to be compared with everything that is there in your, you know, set of signatures. So then how much of work that goes on, okay. So that is why you have IDSs at different places.
Like load balancing.
You are balancing that load. Yes. Okay, simplest answer. Okay, then after that other things will come into picture. Okay.
But counterpoint to that, let's say the packets are going to the left part of the internal network.
Okay.
But the IDS at the, like if you have an IDS like straight down.
Straight down.
The one in that, the DNS section.
Okay.
That won't catch anything that is going on there. So, I mean,
I don't want,
still
because that's a different network, no? See, the blue, that one, the internal network is different and the demilitarized zone, that is different.
Yeah, what is that? What is demilitarized?
That is no particular no particular security is there in that, inside this. Okay, this demilitarized zone. Okay, so that is different from the internal network. Okay, gives the answer. How much time? Oh, I have already increased the time. Okay, so one or two more slides I have. Okay, so next is the security policies and practices. Okay, what are those? Some set of rules that you should have or guidelines that you should have to ensure, you know, how your system, data and network should be safely used. Okay. Now, what are the challenges for using these security policies? That it is difficult to impose such things. Okay. People will resist anything. Okay, so that is one thing. So first thing is access control models. There are various types of access control models, that is how much access you are giving. First is MAC, that is mandatory access control. The admin will decide it. Okay. Next is the data owner will decide the permission, which is discretionary access control or DAC. Oh, sorry. And the last one is role based access control, okay, or RBAC, where permissions will be tied to the different roles. Okay. So these are the three access control models that we have. Okay, and in the end, this is the future, that we should come up with different security policies and procedures, and in-depth computing is necessary, defense in depth. Okay, and last one is the zero trust architecture that I want to focus on. So what is this zero trust architecture? Okay, so this is basically based on the concept that you don't trust anybody. That means every step there is an authentication. Okay, whether every step you are checking that whether I am talking to this person is a trusted person or not. Okay, so there is no trust in this architecture. One way you can say that yes, it is very good, because more and more security is there. What is the flaw of such a system? You have to continuously, every step you have to authenticate, authorize. Okay, so that may be difficult for systems which require low latency. Okay, so this is the future, and I will end my class with this. If you have any questions, please ask.
So the same question, do we need security at every layer, or?
That is a homework question I told, right? Find out. Okay, what do you think after this class? What do you think?
Generally,
Depends on?
Where are we using it? Like, what is the use of the system? Because
Okay.
I shouldn't give a military grade security to a child's laptop.
Yes.
So there is no need for every layer security on that, rather than I should do or wherever it is needed.
Yes. Very good answer. And
same.
same answer. Okay. Okay. So let's see tomorrow also once again. Okay. This is a good answer that I like.
But what do
Okay.
we do in real life? Do we do that whatever we said, or?
That we will find out. Okay. That again depends on what is the system that you are providing the security for. Okay. It depends on that. See, user level security you have to provide. Okay. And then TCP, the transport layer security, if you are going over the medium, over internet, if you are going, you have to provide some kind of security. Then comes the network layer security. Okay. So then whether we should provide like this all layers or not, and then whether I should just give a blanket security. So that is a that's a question, okay, open question.
When you say
Yeah.
blanket security, do you mean just like from one layer beyond, or just to restricted to one layer itself?
No, beyond.
Okay, so let's say
Yeah.
transport enough or network
Network enough.
Network enough.
Yeah. Okay, so these are the references that has been followed. Okay. All right, and thank you so much. So just I want to announce here is that tomorrow's class is at 9:30 a.m. like today. Okay, not 10 a.m. as is mentioned in the schedule. It starts from 9:30 a.m. and it will continue like today. Okay. All right. So tomorrow we will have a tutorial. So if possible, please bring your laptops for my session. Okay. Yeah. Thank you everybody. Thank you.